Okay, welcome everyone to this defense today. My name is Joakim Widén. I'm the professor responsible for the PhD program that this thesis is in. So the defense today is for Reza, who will be examined for the PhD degree in engineering science with specialization in civil engineering and built environment. I think you may all have seen the thesis. Looks like this, with the title "Synergy between photovoltaic power generation and electric vehicle charging in urban energy system, optimization models for smart charging and vehicle to grid." So I will just briefly present the main persons involved in the defense and also give an overview of the schedule for the defense before we start the whole thing. So firstly, we have the supervisors for Reza. So we have the main supervisor, Joakim Munkhammar here, associate professor at the Division of Civil Engineering and Built Environment, same as Reza and me. We have co-supervisor Mahmoud Shepero, who was previously at the same division as postdoc, now at Ellevio. And also I have acted as co-supervisor for Reza. And we're very happy to have here today the opponent on the thesis. So Professor Johan Driesen from the Department of Electrical Engineering at KU Leuven in Belgium. So very welcome. And we have an examination board. So firstly, we have Professor Sonia from the Department of Space, Earth and Environment at Chalmers University in Sweden. We have Docent Daniel Månsson, Department of Electromagnetic Engineering, if I'm correct, KTH. Yeah. And Docent Hatef Madani from the Department of Energy Technology at KTH. We also have a reserve member for the committee. If anything should go amiss, where is he? He's up there. Yes. So Docent Mikael Höök, Department of Earth Sciences, Uppsala University. So those are the main people involved. And I will just briefly go through the agenda. So first, Reza, you will have the opportunity to mention any errata you might have in the thesis. And if you don't have any, that's fine.
I don't have any.
Yep. Okay.
Yeah.
Then we will have a presentation by the opponent. So the opponent will make an overview of the topic for the dissertation then as a background and introduction to the whole thing. 10 to 15 minutes. Then Reza, you will present your work for 30 minutes approximately. And after those, in total, something like 45 minutes, we will have a 5-minute break to stretch our legs. And then after that, we will have a discussion. So the opponent and Reza will have a discussion. And this can go on for as long time as seen fit. So there is no upper time limit. And then when the opponent feels it's all done, it's time for the examination committee to ask their questions. So each in turn of you will get the word and ask questions. And then after that, we will open up for questions from the audience. So do take your time during the defense to come up with some tricky questions for Reza. That would be fun. And after that, I will conclude the session here. And after the whole thing is finished here, Reza will take the audience to the division lounge. And at the same time, the opponent and the supervisors join the examination committee for their meeting. And that's when it will be made a decision on pass or fail for Reza. Yes, I think that's it. So are we ready to start?
Okay.
Great. And you had no errata. So then we start with the...
Yeah.
Oh.
Yeah.
We start with the presentation by the opponent.
Okay, so I'll start. Yeah, I'll close it here. Yes, so as an opponent, it's an honor for me to introduce this topic. How long? Depending on the email or regulation or advice that I got, it's 10, 15 or 20 minutes. We'll see where we'll get, but don't worry, I won't take a lot of time. But anyhow, this topic of the PhD is actually something that fits exactly in what happens now, the so-called energy transition. And this energy transition, sometimes it's identified as the one where we go all the way in electrification. First of all, is it the energy transition? Because if you read the popular press, it's the energy transition. No, it's just one of the many that has happened in the history. To give you an idea, we once went from using wood for burning to coal to oil and gas and so on. In transportation, the main fuel was always animal feed. Yeah. That was feeding our horses, and later on we went to automobiles and so on. But lately, you see that line of electricity going up, and the lines of the fossil fuels should be coming down. Now, if you're in an energy transition that doesn't go overnight, it takes some time. Typically takes generation before it really is settled. And in that period, there's always a lot of resistance. And that's something that we are feeling now as well. For instance, if we talk of electric vehicles, there are always people saying, yeah, but shouldn't we drive with hydrogen or so? And there's historically, it's always been like that. That's actually something in Dutch, my language actually. The newspapers in the 1950s, there were ads when we were stopping with coal and going for oil and gas. There were ads of people saying that burning coal was so much more pleasant and cozy compared to those ugly radiators in the buildings. So you see, nothing has changed. And by the way, at the bottom you see that there was a period when they even were converting steam trains into electric trains by adding resistors, which is a thermodynamic crime. But okay. Now, currently this energy transition is driven by a lot of regulation. It's a coordinated effort. That's a new thing maybe. It's coordinated by a lot of these European directives that are governing the national policies. Especially Europe is focusing a lot on decarbonization, which is actually a bad word. It's actually de-CO2ification, but that doesn't sound very well, so they just say decarbonization. But what is happening in the back is that it's not only for the climate that they do it, but also to get cheaper locally produced electricity, because we also became too dependent from the fossil fuels we were importing, and we were reminded about that so much last year when Mr. Putin went all the way. Let's describe it like that. So now we are in this energy transition, and it's getting accelerated even with new measures to support electric mobility, to have more renewables and so on. But we shouldn't forget that outside Europe, a lot of other transitions still have to get started. For instance, in Asia, they still use a lot of coal, and it will take some time before they will also enter the era of electrification. And a question that you often get then is, but where does all this electricity come from? So electrification is a lot happening on the load side, but also on the production side. And that electricity is now coming from a lot of renewable sources. Not that we do it because we like these so-called green technologies. No, it has proven that, especially over the past years, that they have become also the cheapest ways of producing electricity. That's shown in these curves. The price of solar electricity completely crashed. Wind power, the prices have crashed. There's only one price that went up, and that was nuclear power, because it always got more rules. And if you compare these prices then to the prices of fossil-based electricity generation, like gas and coal-based, that's the graph on the left, there you see that all the recent projects on these IRENA data charts, all the recent projects with renewables, they are cheaper than that dark greenish zone, which is the range of the fossil fuel generation projects. Okay, so we have lots of new technologies. We have policies, and Europe is pushing us to implement them even faster. And in the end, we are supposed to go and live in houses that look like this. We become prosumers, not consumers, but we also produce some power. There are solar panels on the roof. We, of course, do a lot of smart construction as well. We are here also in a group, in a civil engineering group, so don't forget isolation and stuff, that kind of stuff. But what is important for this PhD is that we get the solar panels on the roof, and all of a sudden we see also our cars being plugged in. And the heating of the buildings is done with heat pumps, and some storage technologies show up. There's actually one thing that's wrong in this picture. It's a little detail. It's all the way up here, this chimney. The chimney will disappear. Yeah, that's good because then you don't have shadow on the solar panels anymore. But it's a problem for children. I don't know how it goes in Sweden, but we tell our kids that Santa Claus comes every year through the chimney to bring the presents. So in the future, we'll have to come up with a different story. But okay, that's our problem. That's not for an engineer to solve. So this is the home of the future, but you can ask yourself, how does this all fit together? Because the sun is shining only during the day. You come home at night and then you want to plug in your car. Okay, so that means we have to think of this local balance, and something that we will discuss later on is this so-called self-consumption, because we want to consume the electricity as much as possible when it is being produced. That is the direct self-consumption. But there's a problem. As I mentioned before, the sun is shining during the day, so you get a big peak in the middle of the day. And typically, you have a lot of consumption in the evening, a little bit in the morning, depending on how much coffee you want to make. But okay, so we have a mismatch, and how do you solve that? Do you change your charging behavior? Should we go to more charging during the daytime? But then your car is probably on a parking lot here at the university or at a railway station. Who knows? Or should we use what we call indirect self-consumption, use storage technologies? And another question that pops up then is this home where everybody has a car and a solar panel and a storage system. Is this the ideal? Or should we go for a more citywide view? And then in Europe, at European speak, they use the word energy communities much more. What is the ideal? Should we put a battery in every house, or should it be a battery in the distribution feeder somewhere? How do we share the cost of that battery? Do we create a market then? Do we sell electricity to our neighbors when we are not at home and the sun is shining? So you can see for an engineer, it's a lot of fun, and also for people making laws as well, we discovered. So that is the renewable and citizen energy communities that are now being created. But you see, the storage technologies in here play a crucial role, and this became possible because the prices of the batteries have crashed. Already showed you that solar power became extremely cheap, and now also batteries are becoming very cheap. The past we showed the graph up there. Nowadays we focus on the graph down there, but I usually explain it in a more simpler way to the general audience. Think of a Tesla. When Elon Musk sold the first Tesla Model S, he had to pay roughly $900 per kilowatt hour for the batteries. I have the impression sometimes the sound is dropping. Yeah. Low battery, damn it. Always happens to me. Batteries on a Friday afternoon at university, always a problem. Okay, whatever. It looks like they're working again. So, so Tesla Model S was $900 per kilowatt hour for the batteries in 2011. Now we are 12 years later, and it's more $90. So the prices of the batteries have crashed, and they're not at the bottom yet. And what will be the result? There are now predictions, depending on what source you consult, they predict that by 2025, 2026, 2027, that the electric cars will become cheaper than the so-called regular cars with combustion engines. Will this be the time to switch them? No, if you think smart, you switch before, because on average, the cost of using an electric car per kilometer, depending a little bit on the local gas prices and electricity prices, but for Belgium, Netherlands, Germany, we are usually It's a factor of 2, and that means it's per kilometer. It's roughly set half of the price to drive electric than with fossil fuels. So you will switch before, and the prices of the cars will break even. And we should not focus too much on the CO2 and prices, etc. There are a lot of additional health benefits to driving electric. No NOx emissions, no nitrogen emissions, no fine particles anymore. And it's also extremely quiet, but living in a student town myself, I can tell you that's hard. Because when I drive around with my electric car, the students on the bicycles don't notice me anymore. But okay, that will solve itself. Now, other people will tell me, yeah, but you with your electric cars, why don't you drive with hydrogen or with these synthetic fuels? If I don't know if you followed the news, but last month, the German car companies, they lobbied actually with the European Commission to have also an allowance for e-fuels, for synthetic fuels, because you can, I'm not going to teach chemistry, but you can use electricity to make hydrogen and then turn it into methanol, and then with some chemical magic, you have a synthetic fuel in the end. But that chemical magic comes with a lot of losses. That's why we always say, if you can electrify, if you can directly electrify like a car, like a heat pump, do it. That's the left column. You have a great efficiency, well-to-wheel. If you really want to drive hydrogen, you have like 3 times more losses, or so to say, with the same energy, the distance you cover with your car is 1/3. That's what people will understand easier. And if you really want to go to synthetic fuels and use your old cars still made in Germany, then you hardly can leave the garage anymore. But don't forget, there could be a problem if you switch electric. This is a real picture that we took a few years ago in Belgium. I come from the University of Leuven, that's close to Brussels. And this is actually a police car from our local police. And I don't know if you can see what is wrong here. Don't know if anybody can see it, but usually I get the answer, you shouldn't give your police such a nice car. But okay, that's true. But the car is being charged by a Cummins diesel generator because they forgot to order the charging points on time. And that's something where we are now having problems with, and we are going to electrify, and then all of a sudden somebody realizes, hey, but what about the infrastructure? What about the charge points? What about the grids? Yeah, because we cannot all charge at home. At city level, in big cities, half of the population cannot charge at home. So you need also electric fast chargers, and there you will use your DC technology to charge in a matter of 15 to 20 minutes. But when we are connecting our cars, what is the next step? I mentioned before that we could also use some batteries here and there. Well, let's check where are the batteries. Well, the batteries are actually on wheels. And that's also a concept that's important for this thesis. The vehicle to grid, usually we say vehicle to X, vehicle to whatever, because if you look in literature, they sometimes call it vehicle to home or vehicle to grid or vehicle to building. So whatever, it's vehicle that's being plugged in. And you can also, in theory, discharge your batteries, because from a technical point of view, the power converters in there, they're all bidirectional. It's just a matter of software. And you can also discharge your car. And why would you? Well, if you look at the statistics, your car is parked for 95+% of the time. Yeah, I always tell my students, our cars are just pieces of furniture to put in front of your house. They are not designed for driving because you hardly do it with them. So why don't we use them like a battery? And that's the vehicle to grid concept. But watch out, the battery, it's very unpredictable where it will be, how full it will be. How can you make money with this? That's also a big question mark. Are you going to try to balance your own home or the neighborhood? Or are you going to offer this as a service to the grid operator? You can do a lot with vehicle to grid, but not everything all at the same time. And the big question is also, will the owner of the car be in favor of it? Because that person wants to have a little bit of financial compensation for it. So you also need a market that is fit for it. So in brief, I can close here. So these energy transitions, we are now in the middle of the electrification transition. It's one of the many energy transitions that passed over the last 250 years. But now, to make it working, we have to look at the whole system. Yeah, there are things happening on consumer side, like the cars. There are things happening on the producer side, like the solar power, like the wind power, etc. We should not strive too much for individual optima, just optimizing our buildings, because often from a technical and financial point of view, it's better to optimize at a much bigger level. That's a collective optimum, like the neighborhood and so on. But to make it work, you also need new business models. And a big problem in here is, I'm presenting this as an engineer. As an engineer, it's a great time to have fun with all these technologies, but watch out there in the evil world. You also have policymakers, politicians, etc. And they often communicate in a very bad way about all of this. It's very popular to say that this kind of technologies are costing a lot of money and Brussels is obliging us to implement them. And then the people, the general audience doesn't trust you anymore. So it's also a time for us to communicate correctly about this, objectively about this, because in the end, if you implement these transitions well, we'll all be a winner in this. Okay, so far my introduction, and now we are going to discuss a little bit about a thesis that is with a subject which is right in the middle of what I just presented in this transition. I think now you're taking over again. For a short summary of your thesis.
Check.
Okay.
So my I need to plug this out.
Okay.
Is there a transition or directly to be? Nope. Okay. They're just, yeah. Oh, wow, very comprehensive. Okay. Should we just begin, or Zoom can see it? Yes. Okay. Okay. Thank you for the time. First of all, I'd like to say thank you, Professor Johan Driesen. It's been an entertaining presentation, isn't it? And yeah, I'm personally very honored, and I wish that I can keep the audience entertained for my own presentation. Yes, previously said, the title of the thesis is Synergy between PV power generation and EV charging in urban energy system, which focus on optimization models for smart charging and vehicle to grid. So I will have 30 minutes now. We will just go on. This is the outline of the today's presentation. We begin with background, but to be honest, I think Professor Johan has covered all of them, so perhaps we can skip some of them. And then we have thesis aims, methods, results, and conclusions. So yeah, I have made this presentation, so I'll present it anyway, even though it's already covered. So we today will talk about energy systems. And energy system is a general term. It can be from subatomic level up to galactic level, like really, really small stuff and really, really large stuff. But today, we will talk about the energy system, which is very close to our life, which is the energy system on human-made built environment. We see here, we have cars, buildings, and these all need energy to work. So today we will talk about it. And so when I talk about energy system, perhaps later we will have some technical aspect which is not very universal, but believe me, it's very close to our life. So for example, what we have here is many activity which are consuming energy. We have cooking. Everybody here cooks, I guess, and everybody lighting the lamp, and everybody wash, and everybody heat up the lamp. And for this thesis, I focus on the, as I said, community or building which has solar photovoltaic and also electric vehicle charging. So why solar PV? Why should we have solar PV? Why should we have electric vehicle? So as if you remember previously, Professor Johan Driesen mentioned about the cost decline of solar PV and electric vehicle. But initially, economically and technically, both are not that great. Nowadays it's become competitive, but actually the main driver of having PV and EV in the beginning, at least, is environmental. So we have technical problem if we install PV and EVs, and in this thesis we want to assess the technical improvement by having strategies on smart charging, load shifting, things like that. So to sum up, what I want to say here is that this thesis is about technical aspect of having PV and EV in the power system. That's the delimitation. Then I kind of like repeat what Professor Johan has been saying previously. But let's say today I want you to kind of like remember what you're doing in previous day or in today. Let's see, at 4 o'clock in the x-axis we have time. You're probably sleeping, and 8 you're sleeping, and then in 8 o'clock in the afternoon you've been doing many things. So it's in here, the blue line is actually the load profile. You see here that when you start your day, it increased a bit, and then during the afternoon it's very high, and it's challenged because the power system needs to keep the balance between supply and demand. So during the day, during this time, like the power system, the power producer needs to ramp up the generation to keep the balance of the power system. And then we imagine if we have solar power only produced during the day. You can see here, as I said, this is load profile. So if you have produce something, the load become low. The load, it can be negative. You can see here, it's going down. And then, as I said, it needs to be balanced between supply and demand. So the power producer or the power system needs to also ramp up during the day. It's another challenge of having photovoltaic. So far, technical challenge-wise, it's actually challenging to have PV. It's not that nice. And then we have also electric vehicle charging. Let's say if you drive today, of course, let's say if you want to charge at home, when you should charge is the time when you are at home, and then you stay at home like from 8 in the afternoon in the evening until the next day. So basically, once you come home, you want to charge, and then it adds the load, the load in your house. So the challenge of like ramping up is then become more challenging in this case. So that's what I want to say. The integration of PV and EVs technically is challenging, and what are the impact of having PV and EV, the mismatch. So this is quite dramatic, but I would like to say this anyway, because I mean it's perhaps more you can just relate to it. So if we have unbalance, we can have power quality in the power grid. Now I would start to say something which is perhaps not really universal, but we will have voltage deviations, and for example overcurrent, and in a universal way it can damage your appliances, and you don't want your appliances to be damaged. So, and then it can also induce power losses, and power losses also equals to economic losses. And also you can have component overloading when you charge too much or you produce more. You have over generation, excess generation. You have overload, and yeah, it can heat up. This is dramatic, but yeah, it's in the worst scenario it can happen. So, what could be a probable solution? So I will just go directly. I don't have so much time, but if we have energy system optimization, then this can be addressed. So of course, there are many probable solutions, like in policy and economic, but in technical aspect, if we optimize our energy system, then perhaps some of the problem can be minimized, can be solved. We have optimal operation and optimal sizing. As Professor Johan Driesen said previously, if we park cars on average are parked 20 hours per day, which this is a potential because your car's staying there and it's kind of like stationary battery. It's there. There's a potential to use this, and it can be a flexible load. Of course, EVs are for transportation, but yeah, while it stays, as long as you have your battery fully charged when you need it, then it should be okay. And next level, it can be also flexible generation because you can even discharge the power from your battery to the power system. And as Professor Johan said, that it's just software problem. So technically, it should be not a big deal. And yeah, and it's possible to delay charging to match also the EV charging load with the local power generation. If you have PV there, perhaps you want to wait until the solar power kick in. So things like that, in simple terms, that there is a huge potential. And so I put synergy word in my thesis, and I borrowed the quotes from Stephen Covey: "Do not compromise if you can synergize." So synergy itself, by definition, is the creation of whole that is greater than simple sum of its part. And you know that if we have PV, too much PV, we will have over-generation problem, excess generation. And if we have EV charging, we have overload problem. And without synergy, if we just compromise, we can just, okay, this is the limit, and this for PV, this is the limit for EV. In fact, these advantages of having PV and EVs can cancel each other disadvantages and become an advantages. So that's why I put synergy, because if we synergize the EV charging with the local generation, the problem might be solved. It's not pretty straightforward. Of course, that's why I have this research. Then now we come to the thesis aims. We know that synergy can be a probable solution, but it's not pretty straightforward because we will discuss about it later. But from this background, I formulate the thesis aims. So the overarching aim of the thesis is to develop EV smart charging strategy or delayed charging strategy and vehicle-to-grid schemes, and assess their impacts in improving the synergy between photovoltaic and electric vehicles in urban energy system. So I wanted to evaluate the synergy potential in this thesis. And from this overarching aim, I divided the aim into 5. The first of all, I do the review of the state of the art in smart charging of electric vehicle related to PV generation. The second is to assess the PV-EV synergy improvement by smart charging at residential buildings. We can see here that I put red color and italic, so it's the highlight. The first highlight of the first aim is the highlight of the first aim is state of the art. The highlight of the second aim is residential buildings. And the third is to assess the combined PV-EV hosting capacity in residential power grid with smart charging schemes. The fourth is to assess the optimal sizing and operation of PV EV systems at workplace charging station. And lastly is to assess the wind PV and EV synergy in city-scale energy system involving smart charging and V2G schemes. You can also see page 3 in the thesis for the detail of the aim. Now, I have mentioned about the aim, but I want to also visualize the aim. This is the title of the thesis. And we have built environment energy system. We have buildings, houses, hybrid parts, storage, and then workplace, and you name it. And we have 5 aims: review residential buildings, residential grid, workplace charging station, city scale energy system. We want to assess the PV synergy in this with these 5 aims. And it's the thesis was based on 5 appended paper in here. Perhaps you cannot click it now, but of course you can also find it in the internet. So now that's the background and the aim. Now we have come to the method. If I may, I need to drink. Okay, now the summary of case studies and assessment. So the paper 1 is review paper. Of the method is just not just, of course, but reading, analyzing. So there is no really technical method. It's just like review. But the rest of the paper, we have a scientific method, which is done in the paper. So say here we have case study here, and the based on the study aim, we can divide it into 3: load matching assessment, grid study, and hosting capacity and optimal sizing. And you see here that actually, paper 2, 4, 5 doing load matching, but not paper 3. Paper 3 is a power grid study, and paper 4 and 5 also conducting optimal sizing. And this is how the charging schemes which are involved in each paper. So opportunistic charging is uncontrolled charging. So you plug, you charge. It's opportunist. Whenever you plug, you charge. And there's smart charging when you plug and then you wait the best time to charge your car. It can be defined. It can depend on the local generation, price, etc. But for this thesis, it's basically only for to match it with the local generation. Okay, wrong way. And paper 5, we have vehicle to grid. In the city scale, we assess also the impact of vehicle to grid, how it can balance the power and the supply and demand, energy supply and demand within city. Okay, now we have smart charging and vehicle to grid objectives. And in these 4 papers, the objective is technical. We want to evaluate the PV synergy potential. So the objective is to minimize the mismatch between renewable power generation and power demand subject to EV mobility patterns. And in this paper, I formulate as a the objective as variance minimization and least square minimization. You can see section 3.3 in the thesis if you are interested in detail. But I'll just show the how mathematically it's formulated. Is for paper 2 and 3 like this, paper 4 and paper 5 like this. Also, we want to evaluate the energy system performance, but what is the measure? And in this opportunity, I'll also present you the measure. There's load matching measure and assessment framework, and there's also hosting capacity assessment framework. And previously, Professor Johan has introduced you to self-consumption, self-sufficiency. Perhaps I will go more on a bit detail. So let's say, imagine your house, you have your load profile, and you put your solar power in your roof and on your roof. So in the grayish area is your load, and yellowish area is your generation. And we have this measure, self-consumption measure, which is the total of your local generation, which is self-consumed. So you generate, you consume, compared to the total generation. So it's C plus B plus C. This area divided by this area. So that's your self-consumption. And there is also self-sufficiency. How sufficient is your power generation in covering your load? It is actually the self-consumed electricity divided by the total load. So in simple terms, it's like that. And we know that, let's say, if we increase the generation, for example, the yellowish is become like this, you can imagine that actually the load which are covered by the generation is higher, which means that the self-sufficiency is higher, but the self-consumption become lower because you have like unconsumed electricity, unconsumed power, solar power production. And vice versa, if you decrease your generation or if you increase your load, let's say, just draw the consumption like this, and you see that actually the self-consumption become high because like it's all covered, but the self-sufficiency, the amount of load which are covered by the area is lower. So in simple terms, you increase, if without load shifting, you increase self-consumption, you decrease self-sufficiency. And actually what I presented in my previous study is that I proposed with other co-authors a metric which represent the balance between self-consumption and self-sufficiency with this harmonic mean. Because we know that if we increase self-consumption, the self-sufficiency might be decreasing and vice versa. So if we have some value which can have an optimal, it looks like a convex system, graph, then it will be a technical optimum. So this has been one of the important contribution in my study, which I use in paper 4 and 5 later. And this can be used for optimal sizing. For example, how much PV should we install if we have this amount of load, and vice versa. How much like load should we have if we have this amount of generation? And we also have hosting capacity assessment. By definition, we can read it together here. It's the maximum amount of new generation or load that can be connected without endangering the reliability or quality for other customers. So in this case, it's like if we install PV too much, then there might be over voltage problem. So the amount of PV which are okay with without destroying the voltage, that's the hosting capacity. Yeah, vice versa, if we have like too much EVs there, then yeah, it's the same way until the voltage problems kick in. That's the hosting capacity of the grid. So and in this thesis in paper 3, the hosting capacity measure is quantified by a voltage profile. Okay, now, okay, 10 minutes ago. Now the result. I think I can have some break. So the first aim is to review the state of the art, and it addressed by paper 1. So we can just go directly to take away from paper 1. We assess 4 aspects in the review paper. First of all is the charging objective. In smart charging objective, we found out that one certain objective can lead to the accomplishment to other objective. For example, if we want to charge, the smart charging objective is to increase the self-consumption, we might have a benefit of having lower charging costs. And for example, lower grid problem, or you name it. So what I want to say here that one objective can lead to the achievement of the other objective. And then we have coordination approach. Coordination approach is centralized or distributed, and we found out that in the literature that centralized charging schemes can achieve higher system optimum, but has more complexity compared to if you just optimize for yourself with distributed charging schemes. And spatio-temporal aspect, the smart charging potentials in different places are highly dependent on the user mobility patterns from and to those particular places. And actually, for the rest of the study, the rest of paper, I focus more on the spatio-temporal aspect of potential of PV-EV synergy. And then last one is mathematical models and algorithm. So we have mathematical optimization and then rule-based. So the difference is that we found in the literature is that if we have optimization, we likely reach an optimum condition, but then it's more complex, computationally more expensive, we can say. On the other hand, the rule-based method might not reach an optimum condition, but it can achieve the immediate goal by following simple rules. Now we come to paper 2. This is the summary. So this is, if you see page 52 in the thesis, this is the daily load profile average in a year for a community with 100 residential buildings with, so A, to the left is the uncontrolled charging, the green one is uncontrolled charging, and this is distributed smart charging, and this is centralized smart charging. And this is the visualization of how flexible EV can be shifted. We can see that it can reduce the peak with smart charging. Smart charging can reduce the peak, you compare here, but in terms of self-consumption, there is an improvement, but not so much. So the reason is that EVs are mostly absent during the day at home when people are working. Now the study is followed by paper 3. We assess a buildings level. Now we assess the residential grid. So if we see page 60, this is the violent plots of voltage probability distribution in different energy management system and with different combined PV EV shares. So in the x-axis, we have different EV share, and in the y-axis, we have different PV shares. So the question is when the problems start to access, and we see that for EV, for the case study, for the grid, for the particular grid, if we have 100% EV, then we start to have some under voltage problem, and for PV, we start to have over voltage problem when we have 100% PV share penetration. But of course, this is quite strong grid. So the important contribution of this study is actually to combine the grid study for both PV and EV. And you can see here, this is how I define the hosting capacity. You can see page 63. This is the graphical analysis of combined PV EV grid hosting capacity. We can just directly focus on the impact of smart charging, the number 2, reddish color. You see that actually the EV smart charging can improve from like only 78% in this case to 150% and beyond actually. smart charging can improve the hosting capacity for EV significantly. But if we notice that for PV, it's very small. And the reason is that EVs are absent during the peak period of solar. That's why it doesn't really improve the PV photovoltaic hosting capacity. But again, this is the case study for residential grid. In different setup, it might be better. And now we come to workplace charging station. So in aim 4, paper 4. And here it is the daily average of PV power production and EV charging load profiles with different charging schemes at the charging station. You can see here that the building load is neglected. So it's just like PV EV systems. And we see here that the black one is uncontrolled charging. And this is how well the self-consumption or the smart charging can be matched with the solar power. So you can see that the potential is quite high there, both for reducing peak load and to improve the self-consumption. So the reason is that EV present during the peak period of solar generation. And in addition to suggest self-consumption assessment, we also try to contribute to present a method to optimally size PP system to the EV demand by having those metrics that I mentioned previously, self-consumption, sufficiency, balance. So this figure should answer the optimal value of how much PV system. Let's say if we have 30 here and we have smart charging in B, 30, and then it's better that we have around 25 EV charging ports, and vice versa. Let's say if we have 50 charging ports, how much PV system should we have? It's around like 55. So things like that. Yeah, and you see that actually the optimal value between opportunistic charging and smart charging is different. So it's important to also consider the smart charging scheme when we want to optimally size the charging station or your home charging as well. It can be also the case. Lastly, paper 5, city scale. It's a manuscript still under review. Hopefully it can be published soon. If we can see page 65, we find here the load matching performance of the net zero energy city when the city have a same amount of energy production and energy consumption, electricity consumption, with 3 different EV charging scenarios. And in this case, we have beside PV, we have also wind. And actually, this figure show how is the optimal share between wind and PV. To the far left, we have 0 wind and 100% PV, and to the right, we have 100% wind and 0 PV. You can see here that if the city is just powered by solar power, the load matching performance is low. So then we increase by having more wind, but then the optimal is not 100% wind either. So with the blue is this opportunistic charging, yellow is smart charging, and red is vehicle to grid. We see that the optimal value, if we have vehicle to grid, for wind is 70% and PV is 30% in terms of electricity production. I just want to show you here the average power consumption. And we can see here that I don't have so much time, I think. So this is just to show you that the wind in blue produce more during winter in January and October, while solar during summer, for example, in April and July. Wind produce more at night and solar produce more at noon. So this is the complementary nature of wind and solar. So that's why it's important to assess the optimal share between the two to match between supply and demand in any level of energy system. And lastly, I think this is the last piece before the summary. We also assess the impact of vehicle to grid in improving city scale energy matching. You can see here that I'll just directly go to the most important. So without battery, if we utilize faculty grid with 2.4 gigawatt hour battery, the performance is similar. It's the same as if we have 1.4 stationary energy storage in the city. So if you see here, like, okay, we can just go directly. And then, of course, I show this figure. It's just showing that to make the self-sufficiency 100% in a net zero energy city, it requires really, really large storage, which might not be really feasible anyway, and it can be costly. So conclusion. The first conclusion is that the PV energy potential in different places and buildings are highly dependent on the mobility pattern, form, and to that particular places. Second is in residential building, smart charging help reducing peak loads and increasing self-consumption, but the impact on reducing peak loads is more significant. And the third is smart charging schemes in residential grid enhance hosting capacity for EVs significantly, but for PV slightly. The fourth aim is answered, and the conclusion is that the PV EV load matching potential in workplace charging is higher than in residential areas, and this make the PV EV optimal sizing more relevant. And lastly, on city scale level, both optimal sizing and V2G play essential roles in improving city scale and generation load synergy, and the role of V2G in improving the synergy is comparable to the one of the stationary battery storage. Thank you for your attention.
discussion about the opponent. And yeah, thesis has been covered in sufficient detail. Okay, please go ahead.
Thank you. Okay. So now I have to interview the candidate. I will ask some very general questions. Some very Now you should hear me. Yeah. Okay. So I'm going to interview Reza. I will ask some very general questions, but also a little bit more detail, some very technical and nerdy, but I also watch the audience. If you start falling asleep, I'll go back to the general questions. So, but let's start with an easy one. Do you have a driving license?
Well, that's hard actually.
Yeah?
No, so I have a driving license in Indonesia, but it's not usable here.
Okay, because I wanted to ask you, have you driven an electric car yourself?
I touched it this year, at least.
Okay, good. No, but then it's then I wanted to ask you, if you look around here in Sweden and most European cities, you have different types of chargers. I also showed them on my some of my photos.
Yeah.
And in your work, you mainly focused on the low power charging, the slow charging, the 11 kilowatts most of the time, the level 2 11 kilowatts. But I just checked it on my phone. I have an app for it. Around here, there's also fast charging stations.
Yeah.
Not far from here, I just saw. So what about those? Don't we have to count them in studies like you did?
Okay, so that should be an easy question. I don't think it is. But yeah, so since what we want to assess is the synergy, and mostly it is delayed charging, even with this low level, we try to not charge all the time. Like we even this is a bit high if we want to really match. So it's just point of, at least in this study, in residential building workplace charging, this fast charger will not be relevant if we want to match with the local generation. But on higher level, like city scale, or even and for frequency regulation, this fast charger might be super relevant.
Yeah.
So that's the answer, actually, if I can put it.
Right. But I'll come back to that later about the fast charging. But another thing that you wrote actually in your text, but you didn't mention it. Of course, you implicitly always mean an electric vehicle, a battery electric vehicle.
Yeah.
But if you look in the text in the beginning, you also talk of hybrids, plug-in hybrids.
Yeah.
What do you think about those? Should we factor them in still, or did you? What is your opinion about those?
Okay, so actually, as you said, it's not explicitly saying if it's really BEV or PHEV, but the idea is to having this amount of battery in the study, which can be contributing to the power system. And in this case, perhaps then what I mentioned is the only BEV here, because we want to assess just like the maximum, the best scenario, we can say.
Yeah.
While PHEV is like perhaps nowadays because you want to be safe in the range of driving. That's why it's still PHEV. But otherwise, the future should be BEV. That's my opinion.
Yeah. And do you think that these PHEVs are they helping us or not in the transition?
Definitely. I mean, perhaps on like user mind or user perspective, they are still afraid of having BEV. Perhaps it was too costly. That's why they start with PHEV with smaller battery. But then, with the development of technology, it might, this PHEV might be 100% BEV in the future. So in transition, of course, it helps. It helps the technical aspect as well. Like the grid might not be ready yet, but then with stronger grid, with more acceptance from the users, I think BEV is the future.
Yeah. I fully agree. But the question is, when will people switch? People are lazy. At a certain moment, they will keep their PHEVs because they're so used to going to a fuel station. And even when the range of the battery vehicles is more than enough to make everybody happy, there are still people who will want the PHEV. And that's why you see a lot of countries now, governments are putting tax incentives to to force people in the right direction. Let's formulate it like that. Okay, good. Now I had actually a few questions about your notion of self-consumption.
Not this year.
Self-consumption and self-sufficiency. Yeah.
Yes.
I don't know if you want to. You had a nice definition about that. Okay.
Yes.
Can you explain a bit more what is actually the meaning of these numbers? What do they mean actually? If you have to explain to your family how you should, or somebody who wants to install photovoltaics and they want to use these numbers to size it. What do they actually mean, and where are they relevant?
Okay, so if a family asks me about self-consumption, perhaps I will just say to them that you have rain, and then okay, just forget it. So let's say if you produce 10, and you just use 9. Your self-consumption is 0.9, and this one is either you give it to someone else or you just remove it.
Yeah.
That's your self-consumption. And if the self-sufficiency, if you need 10, but your production or anything related, it can be candy, it can be your production is just 9, then your self-sufficiency is 9 per 10, and you need one more, and this one should be taken from you buy it from the grid, for example. So, and in this case it was a general case, but in energy that's also the case.
Mm-hmm.
I don't know if I put it correctly, but
that's one way of explaining. But what is the goal? To have a high self-consumption or a high self-sufficiency?
Okay, so we want to have high self-consumption, because if we install the generation, of course we want to use it as much as possible. We don't want it to be thrown away. Let's say that if we don't have any incentive, then of course you want to all consume the power that we generate. And why should we have self-sufficiency? Of course, because if we have low self-sufficiency, then we need to buy the energy from the grid, from people. I mean, if we can, it's pity if we produce, but then our self-sufficiency low, then it becomes that you produce something, but you don't use it for yourself. So it's important also to have the high self-sufficiency. So it means that you can be independent from the external.
Mm-hmm.
And in this case, if we don't have any incentive, that is the ideal case. Of course, nowadays, still in the transition, they give a lot of incentive, because the idea is, okay, induce people to install, but later if everybody installing, then the incentive will be problematic, because technically it's not possible. So I hope I answer.
Now, what you always say we in your answer, but who's the we? Is it an individual household, or is it a city, or is it society as a whole? who wants to have high self-consumption or high self-sufficiency?
That's a good question, and the answer, to be honest, I think we should put context on it, because currently the high self-consumption and sufficiency will be beneficial for the power grid. While we are not power grid, if we can sell as much as possible and it's an incentive, then we don't want the self-consumption to be high. I mean, we can still sell it. But if the incentive is bad, then of course, in this case, we want to maximize the self-consumption. That's why for now, I think it's contextual. But in the future, if we have an established energy system with high renewable, high EV charging, I believe that this technical optimum with high self-consumption and sufficiency can also be an optimum for individual.
Okay, good. Now, what about the following statement of mine? Self-consumption is more consumer-centric and self-sufficiency is more generator-centric.
Self-sufficiency, more generator.
I mean, with self-consumption, it's the consumption. You basically yellow part that you produce in your house.
Yeah.
Self-consumption, maximizing that means you just want to consume all of that. You don't want to send anything into the grid. Whereas with self-sufficiency, it's relative to the gray area.
Yeah.
You don't want to buy from the grid because you want to minimize A actually.
Yeah. So the grid will be happy if self-sufficiency high. What do you mention? Well, actually, I don't think it's the case.
Yeah.
Because I mean, it's a business anyway, so they still want to sell electricity to us. But the power grid operator might be happy with both actually. The power generation, I mean, if a centralized generator will always be happy when they produce power because they sell
Just
more.
want to sell electricity.
Yeah, exactly. So it's also the case, I think, in Indonesia, they're not happy with solar power because they start...
Our countries where it's forbidden.
Yeah. Yeah, so I think both self-consumption and self-sufficiency in the end will benefit the consumer. While for producer, economically, they might be helped. But if the grid is congested, if the grid cannot really address more, add more load or PV.
You touched two important points. You have the individual customer.
Yeah.
I just want to minimize my electricity bill, so to say.
Yeah.
Of course, I need to invest in solar panels, but I hope to get enough money back for them. And then you have the grid. The grid, they just want to not have it overloaded, but on the other hand, the grid people, how do they get paid in Sweden? How do the grid operators get income?
If it's a question for me,
yeah.
I mean, I think at least I get a bill for distribution grid, and it's actually more or less linear to what we consume.
Yeah. So it's part of the kilowatt hour.
Yeah, exactly.
That's what I mean.
Yeah.
So if you don't consume a lot of energy, the grid operators don't get income.
Yeah. It's bad for them.
Yes. So solar power is something they don't like because you might also see it like this. You're sending power back into the grid. That's B.
Yeah.
That's allowed here.
Yeah.
And later, as A, you will get it back.
Yeah.
And do you have a net metering system here or not?
Here in I think so. Yeah.
So that means you don't have to pay them. Because B makes your meter spin backwards and A spins it forward.
Yeah, but
you've used the grid twice.
Yeah. But then the grid, we pay grid kind of double for the distribution because we use the grid. And I mean, that's the case.
Okay. Good. Now, you want to maximize self-consumption. Eh? That's one of the goals in your optimization problems. You actually make a kind of mean between self-consumption and self-sufficiency. I think that's a very original way of approaching it, but we'll discuss that later. Now, self-consumption, to maximize that, you only consider shifting of loads.
Yeah.
But what are the other ways that you could use to maximize self-consumption?
Yeah, we can use storage.
Yeah, that's the indirect.
Indirect consumption.
But what else can you do?
Let's see, either flexible load or flexible generation and storage.
There's another one if you look at the picture.
Okay, what's that?
Can you do something about the yellow part?
Curtailed. No, not curtailed. I mean
curtailing.
Curtailing is
curtailing would be that you cut off.
Yeah.
But can't you spread it out?
Well, I mean, without storage, I don't think we can spread out because it's nature of solar energy. It's uncontrollable.
I'll formulate it differently. What is the optimal orientation for solar panels?
Okay, good question. Well, I mean, in terms of energy production, of course, it should towards, let's say, if it's we are in the north now in Sweden, so it should toward the south, like around 40. But of course, that's in terms of energy production. Then your yellowish area will be high.
You get a big peak in the middle.
Yeah, exactly. But then if we want to maximize the matching, we can make the solar phase to the from east to west, for example. But then the energy production will be compromised, but the matching better. Yes.
That's it.
Yeah. But then again, I mean, I don't know if I should state this following statement. But then still there is some potential loss of energy production in that case. So it can be ideal or non-ideal. It's contextual. Yeah. I said, but for your home, I mean, if you don't get incentive, you better face your solar PV towards the west. When
it depends. If you have a net metering system, you want to maximize C. So if you can lower the yellow part, spread it out. For instance, by using east-west panels, or think of in the US, in Texas, for instance, they favor west-facing panels because the peak is in the evening.
Yeah,
shift to the right. So you see, it's not just maximizing energy. You have to think of it in financial terms, and that's why I asked about the net metering. Will Sweden keep net metering, or will you go to a digital meter system with more variable prices or asymmetric prices? Do you know about that?
So the direct answer is that I don't know. But I mean, now the prosumers can select their pricing for electricity. So the future is that we are more involved, and we can optimize if we have solar power in terms of economic, because now we got the option. So whether it's net metering or digital.
Yeah, but in the digital system, you see that most countries now go towards an injection price, which is different from the consumption price. So you can inject the extra power at a lower fee, and there's a lot of discussion. People with solar panels are complaining that net metering was their right, and they had that it was better in the past. But okay, whatever. That's politics. We went through that in Belgium, now Netherlands, going through that stage, and all European countries will discover that people with solar panels can complain a lot. Okay, but yes,
Change the microphone a bit.
Is there a problem? Does it drop all the time? Okay.
Then we can charge as well here. I mean, it's perhaps running out of battery.
Okay, I hope this one is better. Also, the people who design these things don't count for people with glasses, and they are. Yeah. To imagine when I was teaching with a mouth cap 2 years ago, my ears were just too small. But okay. Now, that. Another assumption you make, let's stop discussing about the self-consumption, because we go to politics very quickly if we keep on discussing about that. But another assumption that you made is the driving patterns. You use driving statistics in your work. Mm-hmm. I think they come from cars that were metered or questionnaires to people, I guess. But you assume the driving patterns will not change in the future. Now, do you think that is true? Why will they not change? And if they change, in what direction might they change?
Well, actually, we have a recent dramatic event in COVID, and so the short answer is it's changing. After COVID, before COVID, it's just like business as usual. During COVID, it's like extreme change. People don't go anywhere, and I mean that's basically, if you have EVs, mostly it's a stationary battery because you don't go anywhere. But now things are getting back to normal, but not fully. Now I think many of us working from home 2 days a week, so it's changing. Yes, it's changing, and perhaps, I mean the methods that I presented will be still relevant, but then more case studies for similar method might be needed for the future. So it's your question is quite intriguing.
I think. But if you look at the general trends in car ownership, for instance, a trend that people in traffic sciences observe is that you go for more shared ownership of cars. Now, how will that affect the charging patterns?
Of course, then there will be less people using private car and less energy demand for transport. Then, so it can change the power. I mean, we have been in a massive transition from electric cars towards let's say EV cars, and it's not the end. We have also shared mobility, shared transportation. So we have many things happening simultaneously, and I think now it's just each research is fruitful. I mean, so everybody's doing the things, and at least for this case, is the case of having regular mobility. But I'm aware that actually many things are also happening simultaneously.
It's true. It's there's a big discussion about shared cars.
Yeah,
shared cars are used more, so they're on the road more. So there's less time for them to charge, and they'll need to charge quicker because the next person wants to use them again with a full battery. So that's a trend that will push you away from home charging, in fact, the slow charging. So that's one of the things. And what about if we zoom out a bit, if you've only been looking at personal cars, private cars that people use to move themselves. But what about goods transportation? Don't you have to account that in somewhere in your studies?
You actually, well, now it becomes a not personal, but a contextual answer. But I really wanted to include everything. It's just the data that we get only limited to personal use. Well, actually, it can be for my postdoc or my assistant professor, things like that. But I'm super interested to include many things, and it has different mobility. It has different energy demand, and actually, at least for public transport as well, we haven't got data, but I think Chalmers got a lot of data in public transport. So I'm looking forward to collaborating.
Not public, but also goods transportation.
Yeah, goods transport. I mean, with trucks,
vans.
But I think good transport is much more energy consuming.
It is. Yeah.
So then the potential of the synergy is more on the generation side, or like, let's say, I mean, it requires fast charging, for example, because it cannot be charged with slow. It can take forever. So the thing is, the potential synergy, this is of course the hypothesis, will be a bit challenging because it's actually high consuming. It's less flexible. At least that's my hypothesis. So I mean, I'm happy if I get the data to assess it and prove it.
Yeah, I think it's a subject that is still we are just discovering now what the impact is. But if you look at the amount of energy that will go to electrified personal vehicles for countries like Belgium, Austria, Netherlands, we know the numbers. It's between 5 and 15% extra electricity that you'll need.
Mm-hmm.
But if you extrapolate to all goods transportations, you get very scary numbers. I've seen studies that say it could mean 1/3 extra electricity production that you need for a country if all the trucks go electric. So, but that is still under investigation. It's the numbers that you use to scare off grid operators when you're having discussions with them, and if you want money for studies from them. So okay, but there's definitely a drive also to electrify that. Like here, Volvo in Gothenburg, they're building electric trucks already now and putting them on the market. So, and again, as I said in my introduction before, now people are again discovering that they forgot to build the I think it's really my personal electrical field that is building. But now we see that again, in say society discovers that they forgot to install charging stations for trucks. But that's another thing. Okay, good. Now. Another point in your assumptions, if you talk about storage in your papers, it's always vehicle to grid, actually.
Mm-hmm. Yeah.
But what about home batteries? Why didn't you include those? Do you have a specific reason to not include home batteries in your models?
Yes. Yes,
I'd like to hear why.
Yeah. So actually, the idea is to assess battery is costly. Of course, the costs are now going down, and it has like some issue also with the limited material. For example, now my colleagues here, for example, working towards the less rare material. But the motivation of not including a battery was simply because we want to assess the pure synergy between local generation and the mobile storage that you have. It's not intended just only for energy system, but it's also for the transportation. So I mean, it's kind of like you have a thing which the primary objective of this thing is something else, and then in the meantime you can do something else which is beneficial, and in this case is this vehicle. So that's the motivation. And also, I mean, I mentioned that I did not include any economic, but battery is costly most of the time, at least.
It is costly, but solar panels are also costly. Electric cars are costly, but if it can help you improving, why not?
Yes. Then I think the more relevant study for battery is to always include economic aspect. And in that case, I did not. It's just like pure technical for EV and EV. Because it's kind of cheating. If you have battery, then you're at least for technical point of view. Technical point of view,
Yes, indeed. So you only look at the demand side flexibility in this case. But don't underestimate batteries. A lot of countries, they're very important also because you can get subsidies for them. Problem is a little bit, it's what you say, it's economic. When do you get the payback for the extra investment? In a lot of countries, you need at least 10 years to get the payback. And then the question is, will the battery still be alive after 10 years? So, but it's also a lot of emotion that comes with it. A lot of people just want the battery to be more independent and they don't want to give away the free electricity to the grid, whatever. Not every decision is a rational one. Okay. But I may ask more questions about batteries later. But then another thing that you showed in your introduction was the duck curve. Hope you know what I mean with that. Yeah. Here.
Oops.
Yes, this one. Yeah. By the way, for the audience, they call this the duck curve, if you have a lot of imagination. The new word for it in the US is the canyon curve, because they're hitting the bottom and it's flattening out at the bottom. So, in some places. What is actually the problem with this?
Yeah. Well, in power system point of view, we need to balance the supply and demand.
Yeah.
And if there is a sudden change, for example, in load, there is like frequency increase, and local level you have voltage increase, and then if the frequency and voltage level is outside of the safe range, then it can damage the appliances and the power system. So the power operator needs to scale down ramp down the generation. And it's easy. In Sweden, we have hydropower, but for the most of countries which rely on coal power, it's hard. And it's often that, and then we come to the afternoon when we increase again, and then it's often that of course, hydropower is the fastest. Battery storage is the fastest, like hydropower. Coal power, nuclear is so slow, to catch up with this. And then often that the solution is using gas, because gas is quite fast. And we don't want this to happen. But if we don't use this, then the power system kind of damage.
So if I understand you well, it's not the fact that this curve goes down that's a problem, although some grid operators, if they get paid per kilowatt hour that they transport, their income is crashing. But okay, then they'll ask for another fee. But it's the first derivative of the curve.
Yeah, exactly.
Okay.
Exactly.
Yeah, it's the ramp time, that especially in the evening. Okay, but I was wondering, is hydro really so fast? Can hydro do that in practice? Can you do that every day with hydro?
Well, this is quite a tricky question. But as I said, the fastest is battery. Hydro within seconds can go full power, because you can just release the water. And so the short answer is depend on the ramp, but mostly it can.
Yeah.
And for Sweden, Norway if you generate solar power, you can even receive the hydro, so it's kind of less problematic here. Then.
Okay, but I agree. Batteries are the best. If you look at California, for instance, all the gas power plants are pushed out of the market by the batteries already for reserve. But watch out with hydro. You can do ramp times, but I don't think Vattenfall or so will like you to do it every day. Open up the valves, crashing the water. It's not that easy as it sounds in practice. Good. Then. Another question I had was about this picture.
Yes.
It comes from Matt Bollon. Huh?
Yeah. It's inspired by
the capacity of Matt Bollon.
I don't know if he's here. No, perhaps.
Matt?
No.
I don't know if Matt is online. If so, hello, Matt.
Yes.
Okay,
Yes.
good. Can you give an example of case B?
Case B.
Yeah,
Okay, if it
because
improves
that
in the
means
beginning.
with the way you draw your graphs, things get worse, things get better, and then they get worse. That's how you should interpret that.
Yeah.
Can you give an example of that?
In super weak grid,
Yeah.
radial, towards the end of the line, it's usually always close to under voltage.
Okay. Yeah.
And then when you add some PV, it might not be always under voltage, but then if it's too high, then it becomes over voltage.
Okay.
So
Yeah. Oh, yeah, that's one I did. I thought you meant losses, for instance.
But losses is also the case, actually.
With losses.
I think one of the papers showed the losses curve as well.
Yeah.
Yeah.
Indeed. Yeah, the losses in the beginning, it gets a bit better, but afterwards you derail again. Okay. Good. Yeah, that was my short question. Dan, you also made your first paper was a review on all these smart charging systems. You gave tables, very nice tables about different studies and the different objectives. But one of the things that you actually include there is that you always assume long parking. Yeah, I read it here in your thesis in page number 22. That you always need long parking, so otherwise there's no flexibility. You don't have no opportunity to shift or whatever. So actually, double question: can you do something with short parking? To create any flexibility then?
Well, the answer is depending on your mobility need. I mean, if you're okay with having a battery not full, and then you can just want to contribute. The next trip is short, so I can just contribute and then charge later.
But
So
customers will not like that.
exactly, except if the incentive is quite high.
Okay.
So that's actually the case, for short parking.
Now, the flexibility you're always looking for is shifting in time.
Yeah.
What about modulating power? Isn't that a degree of freedom that you could use?
You mean modulating is like making it a bit low,
Higher, lower?
higher, lower? Yeah. I mean,
Because in the end, energy is the surface of the graph. You shift your graph, or you can play with the height and you make it shorter or longer. Does that make sense to create that kind of flexibility in a big parking lot, for instance?
I think so, especially, well, I don't know if this is like on point, but when we coordinate a lot of car, actually it's much more modulating this power instead of like fitting to the so like each car like charge really high for 1 hour, which is like it can be with fast charging, but then it's kind of like more queuing system. So in the car itself, like more feeling on this modulating power instead of like shifting load. So it's still flexibility. It's just like, but in the end, on higher level system level, we can see it's still not shifting. It's just like each car has spike up, spike down.
Yeah, so it's more an on-off system.
Yeah.
Okay. I agree partially, because if you look at the current cars, there are car brands that only allow charging or not charging, but other car brands, you can literally set the charging level either from the charge point or through an API to the car interface. You can modulate the power. But what if we would be able to modulate the charging power of all the cars? Yeah. Would it be beneficial for the power system then?
I mean, if it's still in one connection point, there at system level, I don't think it's different, but it's more on the car itself. Either if the car likes, I mean, of course, if you charge in the rated power, you have more efficiency, for example. So in system At least to me, I don't think they really care. But the car itself.
Yeah, it's something we still have to learn.
Yeah.
Because indeed efficiency is an important point. That there are now papers appearing where you see that argue that if you always slow charge your car, that you have a lot of conversion losses and standby losses and those kind of things. Even with vehicle to grid, another point that you could improve in your work is, I think, also the efficiency of that. If you look at the real measurements of vehicle to grid systems out there, like the Shademo on the Nissan Leafs, you don't want to know the efficiency of that. It's horrible.
It's coming. Another paper is coming. Quen, Shen, you are here now.
Okay.
Yeah.
Good. But you, talking of efficiency in your studies, you always assumed, I think I wrote it down somewhere, 90% charging efficiency. Yeah. How did you find that number? Was it in a paper or did you measure?
I think it's an average of charging efficiency of one of the charging level 2. Yeah, that's what I found. Of course, this is actually valid if we use rated power.
Yeah,
if not rated power, but that's also like
that's it. At 11 kilowatt, it will be 90%. But some car brands, they start charging at lower powers later on, and then if you would, another recommendation would be also include some field tests and measurements.
Yes,
you'll sometimes find shocking numbers. That also the car manufacturers don't like to hear. So okay, good.
Can I add some point there? Actually. That's why the power module or on-off might be better in terms of efficiency. And if you coordinate the charging like in the higher system level, you can like on-off, while if you only charge for yourself, to fit the generation, you should like compensate it with lower charging level. So that's relevant. And I think actually we have a paper. It's not in the appended paper, like paper 16, or we also like assess the efficiency impact, the non-linearity, and it has some impact, but not that bad, at least for that case study, because we don't go charge below.
And what in that paper, what do you improve then? Do you make the efficiency a function of the power, or what do you change there compared to what you published here?
So it's much more realistic non-linearity, like CCCV. So towards the end, you cannot charge with high power. And it kind of like, what is the impact if we schedule the EV fleets and we consider this non-linearity and we compare to linearity. So the conclusion, if for system evaluation, it doesn't really matter. But for practical, of course, we have to take care of that one.
Okay.
Yeah.
Now, another practical thing is if you have included in your thesis a discussion on the data sets that you're using, like the mobility patterns, you have weather patterns, solar irradiance patterns, etc., demand patterns. But are the mobility patterns and the solar irradiant patterns, are they correlated?
The short answer is...
Or in general, is the mobility pattern and the weather pattern correlated?
Well, mobility pattern is actually more correlated with human activity. And we know human activity, they are active during the day. So, but then, mobility is anti-correlated with the car state, let's say. So, in terms of mobility, it's actually correlated. It's just like when it comes to flexibility of the cars, it's not super correlated.
Okay, and is there a correlation with temperature somehow?
Temperature, yes, actually. Not mobility pattern, but energy needs to run a car. Yeah. So I did not
I'm thinking of Sweden. If you use an electric car in the winter.
Yeah. Actually, it's quite different. Like 15 kilowatt hour per kilometer, 0.15. I mean, 0.15 during summer, and 25 kilowatt hour per kilometer for winter. Actually, I did not include in the whole study. I take care of that in only paper 4.
That's what I wanted to hear. What did you include? Because the numbers that you say, the 0.15, that's like for a Tesla Model 3, that's a summer consumption. But in the winter, what you see now in practice, and there's also papers now being published about that, it's a lot depending on the brands. There are brands that heat the cars with a heat pump, and other brands that heat the cars internally for where the people sit. They have to use a resistor because you don't have the waste heat from the combustion motor anymore. And a heat pump versus a resistor makes a big difference. Also, the battery technology, some batteries like NMC are more temperature dependent. And let's say there are brands that in the winter consume 5% more, and there are brands that in the winter consume 30 to 50% more. So it's also one of those things that car manufacturers don't like to discuss with us. So, okay.
Yeah.
But and what about the solar radiation patterns? Because another thing that was not clear to me, you work with irradiance.
Yeah.
And then you translate that into electricity production.
Yeah.
But also there is a big temperature effect. Did you include that?
Actually, no. In this case, I did not include the temperature impact.
And does it have a big impact in Sweden or not?
I mean, it's not super hot either in Sweden during summer. So, I mean, I did not test it, but I get the feeling that the impact is not that bad.
No, it depends. I don't know the data for Sweden, but for instance, for Central Europe, we know there is an impact. We produce the most solar electricity in spring and in autumn.
Yeah.
In the summer, it gets too hot, and the solar panels don't like to be in the sun, actually. So,
yeah, exactly.
Yeah, that's what I tell my students. Solar panels are just like you. You don't want to go in the sun.
So, if I may add, actually, when we use the real data in, I think, paper 5, it's quite evident that we got more in spring. So, but it perhaps because of cloudiness, we were not sure. Perhaps it could be a one PhD project as well, because sometimes in spring, sun is really bright compared to July. It's always rainy nowadays in July.
Yeah.
So I mean,
indeed, these are all matters of factors of influence. Also the orientations, because the more northern you go, the angles will become more important. And as I mentioned before, there's a trend for east-west panels on flat roofs. And I even discovered that in Norway, there are companies selling you bifacial straight-up panels for roofs and so on. So there's a lot happening there. And again, your self-consumption curve might get a totally different shape. Now, we were talking about the charging as well. In your models, did you assume that people would charge every day?
It differs from paper to paper, but most of the paper, yes.
Yeah.
Except for paper 5, when we kind of use more not realistic, but more like the horizon of modeling is a year. So, but in 3 of the papers, it's like we assume if we charge every day. Yeah.
So, but if you look at the modern electric cars that are now on the market and that are promised for the coming years, is it necessary to charge every day with a car?
The short answer is no. Even that in the study, we noticed that. When we charge every day, the battery barely go below 80%, especially if it's within the city. But again, it's the study was about if we utilize the whole potential of flexibility of the cars. So, I mentioned, I think in the paper, that this is the best case scenario. Of course, in reality, it could be lower. Yeah, I think.
Yeah, indeed. It's again, that's one of these behavioral things that we will have to learn in the future. In fact, you don't have to charge every day anymore with a modern car with 500 kilometers of range. One time a week is enough in theory, but that's not how people think. And again, what I mentioned before, in cities, more than half of the population can't charge at home. So it's their behavior that I think in the end will be very important. But talking of cities and city grids, you used an IEEE reference grid. You don't have to show it.
Okay.
But no, you don't. Yeah. But just for clarification, it's a three-phase grid.
Yeah.
But all the houses, do I get it right that your houses in there are always single-phase connected?
Yeah, it's
because I think you mentioned that somewhere on page 34. Every customer has only a single phase connection.
Yeah, actually, for the test grid, it's the case. Even though in Sweden, actually every house has.
Yeah, that was my question. Is this realistic? Because
no, actually no. Yeah, it's that the data that we have when we did this study is only this test grid. Otherwise, we will use more realistic. And I think nowadays, my colleague also
okay this. Now the house connection is one thing, but what about the charger and the solar connection? Are they single or three-phase inside the house?
It's single, actually.
It's single.
Yeah.
Also for the bigger powers?
The bigger power? Or
yeah. Imagine I put 20 kilowatts of PV on my house. Will it be single or three-phase?
It should be three-phase in reality.
Yeah, I don't know if is there. In some countries, there's a rule, like I think in Germany or so, it's 5 kilowatt above, you have to go three-phase. Below, you're allowed to do single-phase. But there's no rule yet for the chargers. Depends a bit on the car brands. What can they handle, three or single-phase? So, but I think for future studies, this should also be clarified as well. And another thing that I found a bit odd was that you also mentioned there, the voltage is always set to 1.04 per unit at all the time, and the voltage in the substation.
Mm-hmm.
Is this also realistic?
No, actually. No. It was a simplistic assumption. But of course, you can just turn up, increase and decrease based on the axis.
That's it.
Yeah, exactly.
If you have a lot of load in the winter, they could increase it.
Yeah.
But in the summer, if you have a lot of solar, it's actually better to decrease it.
Yes. So it's more generic assumption. That's actually some of limitation in the study. But again, I think the contribution of that paper was to combine the hosting capacity increase and the PV and EP. Of course, the next assumption should be more. Yeah. And actually, if we found out that the grid is quite strong, that's why I was kind of this grid has no problem.
So, that's it. That needs to be checked. I think it will. I think it's really my personal. Magnetic field or so. No, but it's actually, if you just look at the graph there, if that would represent the voltage or so, it's the set point at the beginning that you move.
Yeah.
So it has a big impact on the other side of the graph then as well. These kind of voltage settings, but the question is then, can you change the voltage? You need an on-the-load tap changer in some cases, or okay. But definitely, that's something.
Yes.
Okay. Now then, again, talking of efficiency, I mentioned I would come back to those things and to fast charging. You assumed for the charging efficiency 90%, but that's actually the efficiency from plug to battery in the car.
Mm-hmm.
Yeah. But what about if you have a charging station like you have you showed that also several times, like a nice parking lot in the city or the workplace charging, how would you organize that? Does that also have an impact on efficiency?
Well, if we go step by step, like we have from PV, there is inverter, and the larger the inverter is usually more efficient. And then you have a converter efficiency. So to answer your question, there is also some losses when you convert DC, AC, AC.
Indeed,
DC.
it's then you have to look at it as a kind of a microgrid, and then the question is, how do you organize that internally? There are now technologies on the market that go all DC, others stay AC. And that's also something that I think can always be refined. The charging station infrastructure, but then you enter the dark magic of power electronics in your models. So that's not that easy. Good. Now then, in your optimization, you actually showed also your
objective,
your objective functions,
but not the constraint.
Yeah.
So. No,
objective functions like this. Now, in your overview, your first paper, you actually had a column that illustrated that all these studies have used different objectives. Like some are really focusing on minimum losses. Some are focusing on avoiding peak loads in the grid. But you have something here, what you call this variance minimization. Why did you choose this objective? Why do you think it is ultimately important here?
I know that yesterday you mentioned that you don't like to draw in the board, but I guess I need it.
I think it's a handy objective because you can make it convex, etc. But why did you choose variance minimization? It's smoothing in the end, what you do.
So because we know that actually this EV has energy demand, like it has this amount of energy demand which should be distributed over time horizon. And if we can keep, lower variance, meaning that the load is flat. So it's kind of like both improving the self-consumption and decreasing the potential peak load. So that's why I minimize the variance or the least square. And because if it's close to the flat profile, which is the mean value, like let's say if the ideal is if the load profile is always in the mean value, and if we minimize the variance, then we can have an optimum in terms of peak load shaping and self-consumption.
So it's a sort of a compromise between a peak and but is that then the best? Is this objective then the best for the individual customer, or is it the best for society or best for the grid operator?
Technically, of course, so the short answer for today's answer is that will be beneficial for the power grid operator. But if we look in the bigger picture, if we have technical system, it will smooth out the integration of PV and EVs, massive integration PV and EVs, and more clean technology. So society wins if we have this kind of optimal condition.
Okay. But in the end, if you want to optimize for the individual customer, because in the end, that's the person who will invest, who wants to see a payback on the investments. Would you still use this, or would you alter this somehow, this objective function?
As an individual, we should maximize our economic benefit, the cost, like we minimize the cost. And actually, it's up to the power grid operator or to the market. They should design a market or price signal which make the individual follow this technical optimum. So in the end, actually, this is much more relevant for the power grid operator or the market. The individual is just like they maximize the economic benefit for themselves. But the ideal condition is that if the operator design a price signal so that the load profile can be similar and identical to this.
Yeah. I agree. It's a matter of design and also a bit of political negotiations. But something that I was still a bit surprised about with these kind of optimizations, you don't put a very big penalty on peak loads in the end.
Yeah.
They will be smoothened a bit, but it's not that they will give you a big penalty.
Mm-hmm.
How would you... Yeah, can't you include peaks here somehow, or?
I don't think it's needed, because when you make the load profile as smooth as possible, you are automatically avoid peak loads, and that's the consequence.
That's it. It's as smooth as possible. But if there's one peak a year, one little very big peak a year, it will get through your optimization probably, but it will crash your grid.
If there's a one peak, so that's why we have quadratic, because if you have really large
the quadratic peaks,
then we can. I mean, let's say if we have 10 and it's divided by 2, 5 square, 25 is 50. It's ideal.
Okay,
but then if we divide it 9 and 1 is like 81, 1 is 1. So it's like much more higher. So that's why if we have this objective as flat as possible, it automatically removes the potential of having really high power. If the solver is good. Otherwise, we should not blame the solver, but it's the solver problem.
Okay, good. Now, if you would have, for instance, different tariffs, if you want to include the tariff, if you have an injection tariff or a different consumption price, maybe a capacity tariff, can you also include that in here?
Capacity,
I
mean by
like
capacity.
that is exactly, in some countries you pay pro rata the peak.
Okay. Yeah,
that's what I wanted to say. Indeed, we are entering a situation where it's for your personal benefit the best to maximize self-consumption, but to avoid that, once in a while you draw a very big peak for which you hardly have to pay. Mm-hmm. You get an extra peak fee or peak component in your tariff.
Yeah.
So could you include that in here, or?
I still think that it's automatically removed by this optimization formulation.
Okay, all good. Because, but I have to say, I agree. It's a good approach, this one. But there are, let's say, not everybody is following it, but we have not come to, let's say, a universal conclusion about this yet. Now, let's see. And could you, would you be able to include storage here? Again, I said I would come back to storage.
Storage, yeah, easily. I mean,
easily.
Well, actually. Well, for technical aspect, the storage can, because it's always there anyway. Now I have to be careful because what I want to say perhaps is wrong, but we might not need optimization if it's for technical. Just be there, just put the algorithm. If there is an access, we charge. If there is a overload, we discharge. Simple rule-based. The optimization becomes important when we have limited time of stay of this mobile storage. That's why we optimize the mobile storage first, and then the rest we can use the storage. The storage. That's for technical. If in economical, then of course we should include storage because technical and economic optimum might be a bit different.
But I would watch out if you say it's easy. It might look easy, but what I'm afraid for, and that's actually going to my next question. Now you have a nice convex formula and it will probably converge very well. Mm-hmm. But the moment you start to put in more rule-based control and what ifs, etc., more non-linearities, your optimization might take a very long time. That's actually my next question. Practically, can you tell us a little bit how, because that's something you don't highlight in your thesis, but okay, it's very boring maybe. How did you solve this? What software did you use? What codes? How long did they take to simulate or to converge? Can you tell us a bit more about that?
So it depends on different case, of course. But what I can say is that before I begin with optimization, actually one big task is to formulate the problem as easy as possible to be solved by the software. And that's why quadratic is convex. It looks complex, but it turns out that the machine like it. So to answer your question, it's super fast, like below 1 second per charging session for paper 2 and 3, and paper 4 is because similar. And for paper 5, it takes some time actually because we assess the higher level.
Is it because you have bigger data sets, or is it because there you have the vehicle to grid?
Yeah. Actually, very relevant question. I'm surprised, but yeah, actually, with smart charging, it's much faster than vehicle to grid. In fact, and actually, we try to. Now I don't know it's relevant, but we try to put efficiency. Then the problem become mixed integer quadratic programming, and it takes forever to solve. So we disregard that for now at least. But we'll come back again. Perhaps we.
But practically, what codes did you or how did you solve? Did you use Julia or was it a Python code?
MATLAB and Python. CPX.
Okay. Okay. Yeah. That's not the fastest, I think, but okay.
Yeah. I should aim for more.
But that's a big domain, big point of research for the moment, because everybody tries to solve problems like this. The same with heat pumps, even with heat networks, thermal storage. Everybody's running into these problems, and you see people either going into a kind of model reformulation to go for the holy grail of convexity, and then you can use a fast solver. Or people just use massive computing power, etc. But that's it's still something that is not. We're not there yet, so to say. Okay. And then another thing, if you modeled vehicle to grid, it's actually made a very nice picture. I don't know, you didn't show that.
Yeah.
Can you explain that picture a bit? Like, how did you model the vehicle to grid? Because in my opinion, it is a kind of vehicle to grid, but it's not the only one that's possible. But can you explain how did you model this? Model it this way.
So perhaps I think it's relevant if I open the thesis
maybe
first, so everybody can see.
Not to not show it.
Now we'll see if I have my thesis around. But okay, I hope it doesn't take much time, but let's see which. I go to. Yeah. This. Oh. Which figure it was? 3.5. Then I have to split it up as well.
Page 39 in your thesis.
39.
Yeah. Yep, you passed it.
I can't really see. 16.
Stop. One more. Yeah.
It's upside down, but it's rotating to 90 degrees. So
here it is. Yeah.
Can you see it? Yeah, it's not that ideal, but
okay, but
I mean, okay, I'll try. So actually, in here, the objective of the study is to evaluate the V2G scheme, which is happening in EV fleets instead of like V2G in each car. So it's not that ideal, but what I want to say here is that V2G is in, let's see, it's in the, when we have discharge energy, so the time step, discharge energy, time step 2 and time step 3, isn't it? So your question is, how do I?
Yeah, there is a kind of rule-based algorithm behind this, I have the impression. Or isn't it?
Yeah, so I mean, I think it's relevant if I just put context on it. So since in the end, what we have in the optimization formulation is the charging power, discharging power, and generation power. And this discharging power and charging power is actually the aggregated charging power and discharging for the whole system.
Mm-hmm.
So that's why I use this visualization to give a kind of like what is happening behind. In fact, that actually what we optimize is just the aggregated charging and discharging. So for example, here in this is not super ideal, I'm so sorry, but let's say, and for in time step 2 and time step 3, there is only one car, which is the yellow one, discharging energy. And so in aggregated level, only one bar of energy is out. But of course, I mean, we can just put another example. If 2 cars are discharging, then we have 2 bars out. So on system level, 2 bars out, 1 bars out. So that's actually the objective of.
Okay, but you have the impression in your modeling, you take a more overall view of the whole car fleet.
Yeah.
And that you do a sort of individual car modeling, like a more agent-based modeling.
Yeah. Not for this paper.
Okay.
Actually, my colleague on Sunday, or not my colleague, but my collaborator, also present this model agent. So based on this model, we also schedule each car, and it's actually will be presented in a conference. I think it's paper 16 or 17.
Mm-hmm.
Yeah. And unfortunately, it's not part of the unfunded paper, but at least for paper 5, it's more on system level and how we visualize.
Okay, it's good. Yeah. But I think that an open question is that in how far can you, in reality, obtain this behavior? Because in practice, it's all individual systems with lots of limitations and uncertainties that will be added up. And that is because there needs to be a kind of a rule-based controller behind it. In some cars, there's a limitation on the discharging power. And it's not that they can. There are car brands like a Nissan with a Shepero. They can charge at 50 kilowatt, but they can only discharge at 11 kilowatt. So there are lots of other details that will come in. Okay, but indeed it's an aggregate model. And then to optimize, you used. I also promised I would come back to the self-consumption. You used that kind of harmonic mean of the self-consumption and the self-sufficiency.
Yes.
Yeah, this one. Yeah. Why did you choose that kind of combination?
Harmonic mean.
Yeah. Why?
It's not arithmetic mean. I should perhaps.
But there's geometric mean. You could have a kind of quadratic mean, or there's so many ways you can combine 2 factors.
Well, at least actually, the direct benefit of having harmonic mean is visible if we compare it to arithmetic mean. Not to geometric mean. Geometric mean perhaps is kind of like similar because like you square it first and then you divide it. But for arithmetic mean, I mean, I present here that actually if we have an arithmetic mean of 0.5. So if, for example, if self-consumption is 0.8 and the self-sufficiency is 0.2, the harmonic mean is 0.32, which means that actually it's towards self-consumption more. But if we have arithmetic mean, it's just 0.5. It's not balanced. So actually, and if we have harmonic mean, it's always making the self-consumption and sufficiency balance. So it compensates more the both performance, not just one. Because like, let's say, I mean, the extreme case is if the self-consumption is 1, the self-sufficiency is 0, the arithmetic mean is 0.5, which is actually not the good performance.
Yeah, it all depends. Yeah, your implicit assumption here is that self-consumption and self-sufficiency have equal importance.
Yeah.
But that again, that depends on the business model, on the tariffs, and so on. So when I saw this picture, actually exactly that picture, I thought, what is wrong with Pareto fronts? I can just draw them. Look at the colors. What is wrong? Why didn't you just use Pareto fronts? And in the end, it's up to the regulators and the market to decide what should be the ideal balance between self-sufficiency and self-consumption. And then you know the front on which you have to choose your point.
Yeah, I mean, there is no wrong, of course, with Pareto. I mean, perhaps it's much more correct in many cases. It's just a technical point of view. This SCSB might be the best for technical aspect for the power grid, because SC and SS in technical point of view might be more equal than in economic way. So,
okay. Yeah, but I think we could keep on discussing about self-consumption and self-sufficient.
Yeah.
In the end, the answer is that for individuals and for grid operators and everybody, the optimum is different. And then it's a choice of the regulator on who will cover what costs in what way. That will depend how the system should be operated. Okay, good. And then the way you treat curtailment, that comes a bit further. The way you'll treat PV curtailment, because that was in your simulations. You showed the results with the four squares in different colors. One of them was curtailment, but how did you implement curtailment? Well, leave this here. I'll have a next question about this. But
which one?
No, just in general. How did you model curtailment? Because you did not include the grid or so, or just how did you include curtailment?
So there is a super hard curtailment when you can. So let's say in this case, I have green without curtailment.
Yeah.
The green is with PV curtailment. So no excess export load. This is like super extreme case. Perhaps it's much less
do you
realistic.
mean you curtail if your voltage goes over 10% or?
No, it's actually in the green one. It's you don't even curtail excess power generation.
Okay, you don't allow sending back. Sending power. Okay, yeah.
But then with the light blue, it's that one. You don't exit.
Yeah, because I want
10%.
to ask, how does it work in practice? Because in practice, if you have a PV system, the thing will just keep on injecting unless there's a control command that says, stop, or until it senses that the voltage goes out of range.
Yeah, I mean, in reality, we should measure each point, which is not realistic either. So in this case, it's just the assumption, the evaluation. If we include optimal curtailment, like ideal curtailment, without exceeding 10%, how much electricity self-sufficiency we have. So it's more or less little different. For example, in there, so I'm not sure about this. Installed PV share. Yeah. In this case, is the consumed electricity is more or less the same compared if we hard curtail. That's actually the case study. If we optimally curtail, we won't lose that much energy, which is actually quite obvious. So yeah, I mean, it's the schemes, it's scenario, and then in reality, the control guy needs to deal with that.
The reality depends on how the installations are built. There are countries where you have like a capacity tariff, and they will give you literally a fine if you inject too much. Or it's in certain grids you see the voltages going through the roofs and all the PV installations stop by themselves. So okay, but I think the question was clarified. You did that. Good. Now the violin curves.
Violin curve. Ooh.
I love that name, violin curve. I see a totally different musical instrument in it, but okay. Some crazy hard rock guitar or whatever. But
it's better with. I think it will be better with the presentation slide because it's more kind of.
But my question about it is actually quite short. How did you compute that? Because before you mentioned you used MATLAB and Cplex. But here this requires a bit more computation effort, I think.
I use both MATLAB and OpenDSS.
OpenDSS.
Yeah.
Okay.
So OpenDSS is quite hard to manage.
But I combine it with interface.
Yeah. So I use MATLAB for different scenarios, and then it's like takes 3 days. I think for the whole simulation year for a whole year. So I use OpenDSS. Okay, the question was, can't you simplify that? Do you really need OpenDSS? Sorry,
do you really need OpenDSS? Because OpenDSS is, you can simulate so much with it. It's also the transients and fault currents that you can calculate with it.
Well, actually,
in this case, it's a radial grid.
It's radial.
It's a radial grid, so no loop currents. So it's relatively easy to solve.
That's true, actually. It was just like easier with OpenDSS because we already have the model in existing model in IEEE. But we also developed grid in our group and use.
And did you not include reactive power here?
Reactive power was simplified into 0.95.
So you fixed. It was a fixed power.
It's fixed. It's
but in the load flows, because in OpenDSS you can do everything. On balance, you can do AC or DC load flows.
Yeah.
But here in these results, was the reactive power flow in the distribution grid included?
I'm not sure if I mentioned, but it was kind of fixed. At least the household load was with power factor of 0.95. And then EV charger is purely
reactive.
Unity, and the PV is also Unity. So it's just the household load, which is 0.9 something. And then it's just built with the grid, not the PV inverter.
I think your grid was the grid resistive or inductive?
The grid is typically typically like the resistance is like really high compared to inductive. So I can say it's resistive but a bit inductive. I mean not capacitive, of course.
Okay. Yeah, because somewhere in the beginning of your text you actually explained the voltage drops. But if your grid is just resistive, you can again simplify all of this. You don't need to calculate all these reactive drops because they will hardly be noticeable. Okay, whatever.
But there is a inductive component in the grid. It's not pure air, at least in the simulation. So, but it's even though it's so small, and I agree, it can even be neglected because it's too small.
Or
some point.
another trick that is sometimes used is do a quick optimization with all the reactive stuff and then use that as a starter solution for the more complicated models.
Yeah, it's always the case. I mean,
that's also a trick to win some time. So.
Yeah, I mean, for distribution grid, I think it's justified because the inductive component is too small compared to the reactive.
Good.
To the resistive. I'm sorry.
Yeah, but then now I have a question about this.
Yes,
it's out there, or you also had it on the slide. Yeah, slide 33 there. Yeah.
Yes. Yeah.
I appreciate it as a piece of art by Mondrian, but how should I interpret? How should we use this?
So. Actually, the idea is the most important idea is to combine the EV share and PV share, and it's quite tricky with many colors. I mean, if I can draw something here, actually, do we have chalk? so let's just if I wrote it here. I mean, the x-axis is the hosting capacity of EV, for example. And at some point, it's here. But then when increasing PV, I mean, it can go this way or this way. But, I mean, ideally, it's actually this way.
Yeah.
But for residency grid, we cannot really see.
That's my first question. Is it a static or a dynamic representation?
It's actually based on the voltage violin plots. I mean, so it's kind of like static because we just use as that data.
That's you made the violin plots for certain scenarios. Huh? It's a bit like a Monte Carlo simulation.
Yeah.
You simulate a lot. But then the EV share, is that at a certain moment in the day, or is it like in general in the street, how many people have a vehicle already? Is that how you should read it?
So in this case, it's actually EV share is strictly strict. It's the number of EVs exist in the community, and it's already taken out from the statistics. So the coincidence factor is there, and it can change, of course, but it's based on the existing mobility pattern. So I mean, yeah. Because unlike PV power, it's much more kind of like the correlation between one point is high. With EV, it depends on like people mood.
Okay, because I was really confused. I thought it was more a dynamic curve. Like for instance, at night there is no PV, you go to 0.
Mm-hmm.
And at night, you always have to choose between the without EMS or the smart charging only. And if, for instance, during the day there are more cars coming, you go to the yellow zone when the sun comes up. But it's more a static. It's more a kind of curve to decide on the policy to implement. Okay.
Yeah.
But could you make a dynamic version of this? Because if this would be dynamic.
Yeah.
This would be your control model, your highest control model.
Can it be dynamic?
Yeah, in the sense that during the day, if there's more cars arriving, you go from one color to another, or could it be used like that?
Yeah, of course. I mean, it's more like video instead of like figure. If it's dynamic, I can imagine. But of course, if there is a device which define that, okay, now. I mean, EV can be dynamic, but PV you cannot just like put in PV. So, but in terms of EV charging hosting capacity, yes, dynamic is relevant.
Yeah.
So it depends on like now we have so much PV, the hosting capacity of EVs now become higher, so charge more. So this kind of stuff.
Now I can imagine that you can always estimate how much PV there is because you know the weather and the roofs are full. Huh? People, the grid operators know where the PV is, but how do you know how many vehicles are on the grid? How can you find that out? So because in your other paper, you for instance showed that the centralized algorithms work better. Yeah, but how do you get the information that you need?
Oh, well, I mean, of course, the straightforward answer would be if we have like smart meter, but not always. I mean, based on if we plug EV, then there will be change of voltage at some point, at that point. So it doesn't matter if it's about how many EVs. What matters is how is the voltage level in certain point of the grid. So it's more. So if it's here, it's just more universal communication for it.
I understand it, but again, in practice, knowing how many EVs are out there is very hard because you have something called privacy, and just if problem already with smart charging is there's no way you can get information out of the car on the state of charge of the battery. Yeah, because that's part of the privacy of the driver. So the charge points are not allowed to get that information out. So I mean, you need a special app for that.
Yeah, I agree.
Okay, let's see, because I asked already a lot of questions and we're already busy for an hour and a half. Oops, sorry.
It's a very entertaining discussion, I hope.
I know I can go on forever, but I have to think about the health of the people in the audience as well. So good. Now, let's come to a series of concluding questions, because I asked about the methods, about the data, about the assumptions, etc. Also a bit about your vision on the energy transition and the technologies out there. But if I look at your concluding chapters, I was wondering, do you have, if I would ask you to formulate an advice based upon your work to grid operators, what can you advise to them? Because let's start with the grid. I have several other stakeholders coming up, but what about the grid operators first of all?
I think the most relevant suggestion for the grid operator is to design a market scheme or a price signal model. We have this technical, perhaps the user will not like it. So it's your task to design this market so that your technical optimum can be reached. Because if you have technical optimum, you can kind of like
But is that the task of the grid operator? Because the grid operators, they just build and operate the grid, and they'll get a financial compensation for that. They're regulated, so they always get money.
Yeah, exactly. Yeah.
But is it that's for the regulator? Huh?
The regulator, yeah.
Yeah. So the regulators, they should think about a smart tariff then. If I understand.
Yes, smart tariff. Yeah.
And so what components should be in that tariff?
For power grid.
In general, here for the situations you studied, if you have the freedom to design the tariff for Uppsala here, what would you put in or not put in? Or
I'll put in, of course, the methods which are forecasting power generation correctly, so that, I mean, in the end, we should utilize the local power that we have. So my suggestion is perhaps to make sure that if you have local power generation, you should deploy the smart system, like it is smart metering, smart tariffs, smart this kind of stuff. For power grid, perhaps it's smart meter might be the most relevant, because as you said, other stuff it's much more about the regulator. And perhaps that's the case. I can't think of it now, but
okay. And what about the people who own a building?
That's interesting, because actually nowadays there's incentive for green building, for example. And actually now with the increase of electricity price, it's much more relevant to install your local power production within this building. Of course, the idea is to make the building more not self-sufficient, to first to make it efficient, and then second to make it self-sufficient. Now contextual, it's beneficial for them to generate their own energy and even to participate in the flexibility market.
For maximum PV on the roof. That's what I understand.
Yeah. It's contextual, but to be a net zero energy building, it's now beneficial.
But that's difficult. And net zero, you only studied the vehicle here. So net zero, then we have to discuss the winter in Sweden as well. And I think it will be hard to make it net zero.
For building, that's true. Well, net zero. In net zero buildings, it's the heating load that will dominate in practice. But okay, and what about CPOs, charge point operators? Because that's a new party in this game. So
because you're in an individual building, okay, you probably have your own charge point, but you also discuss these workplaces with big parking lots, and there you have typically a charge point operator.
So the most evident answer is that, at least for my context, we have PV. So the suggestion is to optimally size your parking charging point in comparison to local power production. And also we can see that actually the potential of workplace charging station, the synergy and PV-EV in the charging station, or at least in public, is high. So I can say that I encourage them to install more local power production in the charging station. I think it's much more relevant compared to in household, for example. So
okay, and car manufacturers. If Volvo comes to visit you, what will you tell them?
I cannot say for the whole thing, but I guess we should encourage V2G. You said that it's the software problem. I think this has a huge potential from EV manufacturers, so there is no reason not to enable the V2G capability in cars. So that's what
Do you have an idea why they don't unlock this feature?
Because previously it's about battery degradation, and I think the research has been going on a lot in this, and it's not really scientific, so it's not scientific argument from my side, but I saw in LinkedIn that actually the degradation is not that bad. Well, this is not scientific. It's just like still people arguing, and I take this as an insight. So research on this should be always be encouraged, and I think in the end, with more sustainable battery and then less rare material for battery, the future is bright for V2G. So
okay, I think there are two reasons why you can't get it on a car now, and that's indeed they don't like you to mess too much with the battery, and also the charging standards. They are not final yet. For Shademo, it was there from the beginning because the Japanese had made Shademo so that you could use it in case of an earthquake and power your home there. But the CCS standard, the V2G protocol, is not yet final. So, standards are just a compromise between all the commercial parties. So the car manufacturers themselves are slowing it down. So, whatever. That's democracy, they say. Another question I have, very general question. It's you studied here the case for Sweden, say a city like Uppsala, with Swedish data, Swedish behavior, a Swedish regulatory model. But you're from Indonesia.
Oh, hi, Indonesian friends.
Yeah. Is there any lesson from this that you can translate to the situation of Indonesia? Because in Indonesia, the grid is different. The generation this difference. I don't know electric cars in Indonesia.
Yeah. So the homework is different.
Yeah.
I mean, let's just put in context. Sweden is, we don't have well, actually, it's quite a risky argument, but compared to Indonesia, we don't have, not we, of course, Sweden doesn't have the transmission problem. So what I was saying is actually that the hydropower can compensate renewable power generation and transmission level, and the problem might be in the city scale energy system, because that's the grid might not be as strong as the transmission, and then things like that. In Indonesia, there is more challenge from transmission to the distribution. But what I want to state is that there's a potential in Indonesia because their sun shines all the year, and then actually in sustainability context, now Indonesia as state, we still use coal power. So in Sweden, for example, we use solar power, but actually the existing electricity system is already clean. But Indonesia, solar power add a sustainability value much more than to Sweden. And then, people also, the mobility pattern is not that different. But I want to say is that the synergy for Indonesia might be higher than compared to Sweden. So
because of the weather mainly.
The weather mainly, yes, the weather mainly. And also because of the existing electricity is not that clean.
What do you do in monsoon season?
Still better than here. Still better than here. Still we, on average, actually the monthly solar radiation that we receive is more stable than, it doesn't really.
And is it allowed in Indonesia? Do you just put solar panels on your house?
Nowadays, not yet. So we still work. Now it's become policy problem. Then I need to be careful because now I don't know. So for example, previously we have net metering, but nowadays they even limit the amount of PV that can be installed.
Indeed, it's in Indonesia it's hard to compare because you don't have the unbundled models like we have it here. It's still vertically integrated, and then the objectives are always different. Let's
exactly
relate it like that.
I better not to say many things.
Okay, good. Well, I think through the thesis, I think I spent an hour and a half, more or less. So I think it's now the rest of the
good
journey.
Time.
Yeah.
Thank you.
Okay.
Do you want a short break? Any nodding faces? So if we're back at 10 minutes past 4.
Nice. Oh. Is it time to make friends with you now or not yet? Thank you. It's very good discussion.
You know what you're talking about.
But I'm actually surprised that it seems like you read from the beginning until the end my thesis. But
I was supposed to.
Yeah. But okay.
I read the summary, and then I checked the paper. There was like extra stuff in there. I did not read the papers all from beginning to the end. The summary was very good. So,
Thank you. But it's save it after it. We can compliment each other afterwards. Yeah, exactly. Now your time. Yeah, I better not to share compliments now. Okay, go. Oh, it's your time now. Oh yeah, it's another 1.5 hour. You were a student here in Uppsala? Oh.
One girl in the group that her dissertation was after 5 hours. One of the opponents in one of the grading committees stood up and said, "Okay, I have to go to the toilet," and then he just left. I think it was 7 hours.
7 hours. I commit. We have 4 hours to go there. Yeah. Perhaps I need to go to the toilet as well. Yeah. I mean, really some. Oh. Pamit, Mbak. Ya, mau pamit. Ya. Oke. Iya, makasih ya udah datang. Aduh. Tack så mycket. Shoot. Jangan ada yang benci saya. Ini bikin mau melakukan apa saja yang dia bisa lah ya bentar lagi. Iya, dikit lagi harusnya. Time for Do you want to go through the thesis? I mean, in the screen, I think it will be better. The test. Yeah. I was just wondering, perhaps. Okay, yeah. Then I'll I'll make sure I download it so it's. Oh. Now it's with the better.
Okay. Are you ready?
Yeah. Yes.
Nice. Okay. So.
This.
Okay. Yes.
This.
So now we come to the part where the examination committee is going to ask questions. I will hand this microphone to you in turn. I think I will go by this my list here. So first we have Professor Ye from Chalmers University. So please.
Thank you. Okay, so is it working? I think so.
I think so.
Good. So, yeah, congrats for giving such a good presentation and very intensive 2 hours of to the opponent. I enjoy reading your thesis, and I also enjoy the discussion with the opponent. The opponent was super thorough and extensive. So I have 3 pages and no, but I cross out every single one of them. Kudos to the opponent who asked really good questions. So I think I would ask you kind of a high level question that and mostly come back to the same points that the opponent have asked you, that there's this kind of trade-offs between individual optimum and collective optimum, and the consideration of business models and behavior aspects and so on and so forth. So and you're moving, your whole thesis focuses very much on the idea of self-sufficiency and self-consumption. The opponent had challenged you from various different angles about this key concept. That's the cornerstone of your thesis, and I'm going to do the same as well. So as you move from paper 1 to paper 5, as your system boundaries become bigger and bigger, it seems to me there's no point to consider self-sufficiency at the individual level. And that almost make your paper, as you move from, paper 5, from 2 to 5 at a system or community level, you almost make the point in paper 2, 3, and 4 obsolete. And I don't know. And so I wonder what's the point of them? Are they become pointless when you move to the system level? Or it just a personal learning journey, learning how to model? Or you still think there are points in the paper 2, 3, 4 that's still worth considering? So that's part A of the question.
Okay.
Part B.
Can I clarify before we move on? It's on the self-consumption and self-sufficiency or self-sufficiency only? That you
the combined concept.
The combined concept, the balance between the two.
Or maybe self-consumption and self-sufficiency. Yeah.
Yeah.
And then the part B question is, I actually, a week before I come here, I had a team from China. They call me and say, email me, that I have these billions of data points about electric buses in China, Beijing, and I want to study this problem. That I also have a solar radiation data for China, for Beijing. So I want to study exactly the same way you formulate your problem of I want to see formulate a self-sufficient system of solar generation and electric buses. And I spent an hour convincing them not to do that. I wonder, what advice would you give them? What kind of research question would you advise them? Do you think they should study the self-sufficiency between solar and EV buses, or you would advise them to a different research question?
Yeah, that's okay. That's the first two, I guess. So I think it's worth doing that, I clarify your question again. It's quite long. So the first is like from paper 2, 3, 4, 5, it seems that we found out that this self-consumption and sufficiency become less relevant. And what is my opinion on that? So, I mean, actually, I think, well, of course, we know that self-consumption and self-sufficiency is just a measure. And actually, what's the challenge, real challenge, is let's say, the power system itself. And I don't think that this is irrelevant, because when you consume power, the self-consumed power, there is self-consumption and sufficiency. The grid problem is actually reducing. So, I mean, from technical point of view, actually, this is for the benefit is quite technical. So what I can say is, to me, it's still relevant. It's just like perhaps it's more relevant to one actor than to the others. And for system point of view, of course, if we have high self-consumption and sufficiency and both, then we can integrate more renewable energy, more high consuming loads in the system, because it's the challenge of the electrification. So I don't know if I answer question, or I mean, if I missed the point of.
No, you addressed the point.
Yeah.
Hear how you argue and what are your rationale. So you can move on to the second one.
Okay, the second is about Basis Solari convince 1 hour not to do that to these people. In my opinion, it's contextual. Perhaps you know better the condition there, but given just the argument of why should we do things to make the electric buses self-sufficient with solar power, then we can mention several stuff. It's just like me from being a scientific point of view. So if we have electric bus, then we will increase the electricity demand in the power system. Then become one challenge is that you need more energy. Of course, you can install coal power or any fossil fuel based power plant, but then it's sustainability wise it's not good. So let's try with solar. And I think, of course, it can be solar, it can be wind, it can be hydropower, as long as it's like sustainability wise it's good. To me, go on. So I don't know if there is something behind that, but to me, to study synergy between solar power and electric buses is, I mean, at least for study wise, it should be encouraged. But if the result is negative in terms of like a challenge with power system, challenge with many other things, then we can also have negative results from that. So that's, I think, my point of view. So personal suggestion, go on. If we find it's negative, then we stop. Yeah.
I asked you to clarify what do you mean negative.
Negative, for example, if it's not good that if we use solar power for bus, because then buses should be charged, for example, during the day, and it's not possible anyway. So or if we should have battery, in that case, stationary battery, and then the cost become too high. If there is another option of having more matching naturally matching power source, then we should aim for that. So it's contextual for me, but I think to do the research, I think it's like open questions, and then we will get if it's positive or negative in the end. So for me, research-wise, I think I will encourage them at least to do research first. So I don't know. Yeah, that's my suggestion. Yeah. Okay. Yeah.
Thank you very much. As mentioned, most of the questions were already asked by opponent. So there was, but I will stress a little bit on a few of those points, basically by just asking you. There were several ways discussed so far about maximizing self-consumption or maximizing self-sufficiency. What is the easiest way in your mind to maximize self-consumption?
Easiest. Is it self-consumption or both? Or
No, just self-consumption now. And my next question would be self-sufficiency.
Okay. To install very small amount of PP. Yeah.
And what is the easiest way of maximizing self-sufficiency?
Not to consume anything, and then we have some of like small power. Yeah.
So, and then when you say that doing this both, I mean, if you go back to that table that you had, these combined ones, this table 3.4.
Table 3.4. Okay, I'll start. Yeah.
So if you give a practical example of case A, very high self-consumption, very low self-sufficiency, what would be the practical, case for this one? What do you see? When does this happen?
If we really have quite small generation, yes.
And then what happens in the case C?
If we don't consume,
or just have a large,
having very large power, yes.
Have the same 0.32 for
For
both of them. So you have this SC, SC is the same.
Yeah. So what's the point?
Yeah. So do you see the very large difference for the prosumer in case A and C? What is the large difference between these two cases?
Where for A is that you buy more electricity from the grid, so it will become a economic disadvantages if the electricity price is super high. While for C is that you sell a lot of electricity to the grid and it becomes economic disadvantages if they don't value your excess electricity.
A huge difference also in the capital cost, right?
Exactly. Yes. Yeah. Exactly. Yeah. I agree. Yeah. I mean, when it comes to the installed local generation, of course. Yeah.
This matters a lot. A lot of things of these things that are discussed comes back to the economy.
Yeah.
And then it would be, I think understand that you didn't go that way because you just focus on the technical issues. But was some easy ways to do some guesstimation of the economic implication of those to see what would be the impact?
The impact in terms of economic?
The life cycle cost.
Well, actually, it's tricky. Perhaps I need to think about this a bit more. But let's say economically, we compare it to the. I mean, of course, in the end, it's just like revenue stream, or if we do some like simple cost calculation on like this is the capital and then this is your cost along the way. So it's like economical study. I mean, it doesn't have to be super advanced, but it's just like if we use Excel, I think it's quite easy to find out.
Okay.
Yeah.
And then my second question was that is like also you mentioned during the defense also aligned with what you were saying when we discussed so much the self-consumption was that is that you were saying during the day if we have a lot of PV production and then it can be, if you don't self-consume it, it would be thrown away. So that was a term that you used also. Do you know, in Sweden, considering the Nord Pool price, how much is the price of electricity during the middle of the day compared to the late night?
Actually, it's currently still a bit higher than the midnight, as I recall, or because I think not so much PV nowadays, but when we have so much PV, I believe the price could be even negative. But I think I read the news that recently we will have negative price. I think it's because of wind. I don't know. I'm not sure. But yeah, when we have too much generation, eventually the price will go down. Yeah, but for now, when it's still nobody use solar. Now it's actually quite massive compared to previous years. But I think it's still beneficial economically to sell with the current trend. Yeah.
So it would be, could it work that is like you even as a prosumer you
gain
use your
economic
advantage to sell to the grid during the middle of the day rather than self-consuming?
For now, yes. But now I think the question is for now, so then it's yes. But if we have more PV power later, then might be it more worth it to self-consume. And of course, the study nowadays, at least in my paper, is about net zero city, net zero stuff. So if this net zero is realized, then this scenario of having negative price might be more relevant cases.
Yeah, I don't get as of the opponents was saying that I don't get to net zero, because net zero, in Sweden you can easily get net zero over a year.
Yeah.
But, so net zero over what period are we talking? So then it's also, that's a challenge. So, so you agree that it's like also in the middle of the, in the spring or in the autumn, when you have still very high heat demand in Sweden, which means that it's like you still have a lot of, so the negative price that does, it's hard to imagine that happens in a very cold, sunny day.
In cold, sunny day, yeah, I think negative price will not happen. It's cold, sunny day. It's
so then it still could be advantages.
Yeah. To sell.
Yeah.
Yes. Yeah. It's contextual, I believe. And for the case of Sweden, perhaps that is the case. And in other part of Europe, you also have AC, air circulation, air conditioner. So it's always contextual.
Yeah.
That's it's just one of also the justification why I keep the study technical, because it's always contextual when it comes to economy.
Okay.
Yeah.
Thank you very much.
You're welcome.
Thank you. Okay, so I'm not going to get stuck on the self-consumption, even though I had a lot of questions on that, but everybody has answered them. But I'm going to use the picture.
Yes.
Page 13 there. So
page 13.
Yeah, on the
power grid.
2.6 on the schematic outline of daily loads and so.
Sorry, page 13.
Yes,
right?
1-3. There it was.
This is not the picture.
Next one. This one. Yes.
Yes.
So I was wondering when I'm reading it. So do you think this curve for the daily load, is that a good representation of a household? Would you say that this is a typical or?
Household?
Let's say a consumer. We skip the prosumer.
I think it's okay.
Because I would say this is more if you have aggregated consumers together. If you go into detail looking at, of course, this depends upon what the discretization is on the measurement.
Yeah.
You really don't get this nice curves. It's much more. So my question was really, how much variation did you use for the different houses in those papers at the end, where you have several houses in the city, for instance? How much did you vary it?
Actually, what I can say is I use Widén's model. I don't want to make him being involved here, because I need to be responsible for my choice. But yeah, actually, it's not this nice. It's just like illustration. So in the end, it's much more So this is like the average. In reality, it's much more up and down, on and off. So the variation is like we take 100 sample of building, for example, and then it's all different. It's not correlated.
So it's yes, this is what I was thinking. Then I'm going to go to one thing that I was almost sure everybody here would pick up on, or not pick up on, as questions on. If we go to page 68, or actually
68.
71, it doesn't really matter. It shows the same. You can take 71 because that's nice curves with color.
Oops. Oops. Okay, it's close, I think.
Yeah, so if we look there at both these ones and then the pictures on the previous pages, or even the table there, when I read this, I was thinking, what is the purpose of the centralized control? What is the argument of having it? Because the difference is very small.
Yeah. Well, actually, as the centralized is eventually has some challenge, but actually it's more realistic in terms of charging power, because it's just on off. So let's say we have 30 EVs, and actually the scheduling is more like, okay, now this car should charge first, things like that. But when it's distributed, of course, this is the simplification here, that I assume that actually the charging level can vary greatly, where in fact actually, the lower the charging power is, the more inefficient. So actually, yeah. So the point is that this is depend on you. In the end, actually, both are relevant. And what I can say is that distributed charging, if you cannot manage to have efficiency fixed with different level, this might not be the case.
Because I was thinking on the argument of integrity, it's easier to have a distributed control system at each user and kind of taking care of their own, compared to having a centralized control.
Yeah.
And of course, I imagine, but I might be wrong, but that also is a more costly system.
Yes, exactly.
When I was checking the numbers, I was surprised that there wasn't bigger differences.
Yeah.
But it might come out to that.
Well, I can say something here, actually, because in the distributed charging scheme, in this case, we actually divide the PV generation evenly. That's why it's always close to communal optimum, when in fact actually one house can have really large PV power, or the other has like a super low. So it's contextual, and in this case it's the best case scenario again. So
okay,
yeah.
And my final question, there was one thing that I was also surprised. We were touching upon it a little bit, and that is on the aging of the storage. How would you introduce that in the objective function if you were needed to do that?
Well, by time, with degradation, then your capacity is kind of degrading, and then we have an constraint of the energy content. The maximum energy content then become lower and lower over time. So, but if it's like scheduling between, you schedule not for the whole year, like one day, and then one day, you can just easily update it in each time. If I address it correctly, but at least in the formulation, we can take it step by step. But if for the whole period, then we can put over time. which is, I don't know if it's convex anymore, but
So the second part of the question is, why didn't you include it if you were looking at the whole year?
the whole year.
Yeah, I mean, why didn't you, even though you have the very small step in the degradation, depending upon how you charge it and discharge it at what SOC and such, and what are the voltage limits. But I didn't see that you include it at all.
No. That's
So I was thinking, what was the kind of argument behind that to keep it kind of?
I might be wrong, but I think just within a year, the degradation might not be that much.
No, because you don't know the situation, how is it charging and discharging. I mean, perhaps you drive it to almost zero in SOC and then up again.
Yeah, that's true. So, and at least actually for the case study here, that the mobility demand is relatively low, so that the battery is not degrade that deep. So I think the assumption will still hold relevant.
In these cases, it is actually valid. And
Yeah, exactly.
Thank you.
Audience.
So much. Okay, then it's the audience left, as you said. So.
Oh yeah.
Yes. So I was thinking, actually, this poor guy up here who has read the thesis and been here as a reserve, maybe you should start. And if you have some comment, even though you're not allowed to make a decision later, but you can comment.
Thank you very much. It was a very nice thesis to read, so I enjoyed it quite a lot. But I have a kind of large overarching question. A lot of these transitions do include a lot of need for infrastructure. We see a lot of changes with climate policy. We see a spectacular expectation on electrification of industry in Sweden with something like 60-70 terawatt hours of additional electricity consumption projected over the next couple of decades. We also see a lot of changes in the way people address various political questions, everything from the Ukraine crisis to reclassifications of what energy sources that are considered green, with, for instance, nuclear power and natural gas undergoing quite significant changes. Would you say that the focus on technical issues is sensible, or could we expect a lot of the more socio-political changes in the market stir up a lot of the assumptions you have made and change, for instance, drivers and the motivations for consumers to act if the markets will undergo significant changes? This is my first question.
Oh, okay. There will be more come. So may I clarify again if it's like, okay, to put it in a simple way, it's the challenge is more technical or social or...
Yeah, and also do we see that there is a consistency or stability in some of the assumptions you have made around markets and optimums? If, for instance, regulations are changed in the next decade or so, this could significantly change the need for investments or the will to do investments for some of these large infrastructure demands that would be necessary for charging infrastructure, as an example.
Yeah. Okay. Yeah, I think this is a high-level question, and it's interesting. In the beginning of my presentation, at least I mentioned that actually the transition has been motivated by environmental aspect, sustainability aspect. Of course, then even if it's like political, I mean, now policy-wise, I think politician needs to argue that this is good for the society, for example, and what is bad with having PV and EVs nowadays. So regardless, I think technical aspect always depend on the mood of the society and then So a healthy society is needed because then, of course, now it's now many things happening simultaneously. But what I can say is that if we still, even in the society with common sense, they will always argue, they will always aim to make the earth more sustainable. I mean, quality is increasing. We have vaccine things that thanks to the industrial revolution. So it's always for benefit of the society. Yeah.
I think it's an excellent reply, and some of these things can be captured in various technical models, and some of them have to be more judgment based or captured by completely different approaches. My second question will be my last question, and it is somewhat of a more reflective question. If you know everything you know about your topic today, and you had a time machine and could go back to the first day of your PhD studies, what would you do differently for your dissertation? Would you start things in a slightly different order? Would you focus more on like reactive power issues, or would you do the modeling in a different way? Would you include more social science into the project? What would you do if you could do it all over again?
It's very hard question actually. Now I start to reflect myself. But so if I can go back, then I think yeah, things can be better, but I think my current, so we can see that there is a lot of research gaps in this world, and for me, I'm taking optimization paths. For example, I will not like I will not take any other part, for example, but then I also optimize what I am good at and what is research gap about. So I think I know my strength. I will still go this way, but yeah, I mean, I realize that I have limited energy. Perhaps what I can nowadays, I have a lot of connection because I'm more confident. So I wish that I can start making connection from the beginning. Just that. So yeah.
Thank you very much.
Thank you very much.
Okay. So did anyone follow my advice to come up with some tricky questions? Perfect.
Actually, there is these things. You want?
Yeah. Yeah. Thank you very much for the nice works. And yeah, as you mentioned, that I work on lithium batteries, where it's like very like hot topic in the global like world. I have a question. Before your model going into the policy or to market, do you think like there are still some aspects that you need to improve from your modeling? And also, my second question: do you consider other like renewable energy competitor like fuel cell or hydrogen energy, which is now like growing up again as like important competitor for your like grid model? I mean by like combining photovoltaic and electric vehicles, because like now like fuel cell bus and maybe fuel cell trucks and fuel cell cars will be like released to market. Thank you.
Very interesting question. Just want to clarify. The first is if I can improve my model. What models? Okay, yeah. So yeah, I mean, I think it's always the problem of people with knowledge. You increase your knowledge, you know better your weakness. Of course, there are many weaknesses in our model, simplification. But then we also realize that we cannot make there's no perfect model. Some are useful. And in this case, we want to optimize between if the model is solvable with the current computer. I mean, or if it's like it's perfect but it takes too long, then we just make a simpler model. But we want to make sure that it's useful. So to answer your question, many things can be improved. And actually, yeah, second question, fuel cell. So, I mean, I don't see fuel cell as competitors because, like, our aim is kind of the same towards like cleaner, more affordable energy system and transport system. So perhaps it's one thing we compete, but it's okay. And also the fuel cell is still electrified anyway. So, and from where would you like make this hydrogen energy renewable? Of course, I think it will be more exciting if the fuel cell can improve their efficiency, because then we can have more options. And in that case also, perhaps fuel cell is less dependent to rare material such as lithium. So yeah, perhaps it's like a let's say simple answer or a formality answer, but yeah, I'm actually more excited to have more technology that we can realize our societal aim. So that's all, I think. Now I'm getting lost also in words. But yeah, that's a question.
Thanks. Okay, anyone else?
Over Zoom, perhaps no?
Yeah,
Less?
do you have any Zoom questions?
Yeah, no, actually.
Okay. Thing is covered, maybe. Great. Okay, then I think we conclude this session here, right? So what happens now is that opponent, supervisors, and grading committee, we follow Joakim Munkhammar to the room we have booked. The rest of you follow Reza.
But it's still towards the same building, no?
Maybe it is, yes. I don't
No,
know.
I think we wait 5 minutes.
Okay, then we all go to the same place. Yeah, great, and thanks to everyone involved, and thanks for all listening.
Kita pindah ke ruangan divisi. Dedi Mumtaz, jangan dulu log out ya.